Hello, everyone. Welcome to the third day of the workshop Elliptic and Beyond. I'm very happy to see so many people connected virtually. I hope no one is hungover from yesterday. Before we start for today, I want to advertise the discussion session tomorrow based on the topics that we are going to cover today and the talks that happen previously and which are going to happen in future, making a connection to every talk, but based on the talks happening today. So, and the rules for the talks are, so if you want to ask a question, just raise your hand, and at the end of the talk, you will be given a chance to ask, or depending on the speaker, if he doesn't mind any interruption, you can also ask in the during the talk. So let me start by inviting Harald to share his screen. Okay, so the first speaker for today is Harald Ita from Freiburg, and he is going to talk about vector fields and integrals. So without further ado, let me just mute myself and stop my video, and yeah, the stage is yours.
Okay, thanks a lot for the invitation to talk. And yeah, so I want to I want to talk about ongoing work with together with my student. It's hard to point here apparently. Together with my student Max Klinkert, and yeah, the general topic is vector fields and integrals. Yes, so as a brief introduction, I have to say that I have not worked directly on elliptic integrals. So in the context of the problems that we encountered recently, I tried to find a few pieces that we learned, which might nevertheless be of relevance for this particular topic, so for elliptic integrals. So I collected a few things, and I hope some of them are new and some less new, and I hope that somehow these structures will be of relevance or helpful to someone. Okay, so I will start with a general motivation. So the bigger picture, the thing that we are after are scattering amplitudes, maybe even cross sections, but let's say at intermediate step, scattering amplitudes. And these computations are, of course, very complex typically, given the number of pieces that go into these computations. And one particular piece that we encounter are, of course, the integrals, or associated to them the number of integral topologies. So there are many such pieces, and typically one needs an automated way to deal with these things. Okay, so computing integrals, as we learned in the recent years, or rediscovered in recent years, have a lot to do with algebraic geometry. And recently, we have made a lot of progress with understanding algebraic or using algebraic tools, or extending our algebraic toolkit. However, it has been difficult, I think, or at least for myself, it has been very difficult to activate the geometric understanding of that's involved in these computations. And so I think very useful, so given these issues, in particular the complexity, one would now like to try to find ways to access more geometric information, however, probably to rely on the algebraic tools that we have in order to get there. Okay, so I want to then use one of such tools, and that has not been discussed in literature too much. This tool, this vehicle that should get us to maybe geometric properties are not the advertised vector fields. Okay, so I will try to add another algebraic tool and try to extract some geometric properties from studying these. Okay, so that's the general plan. And in order to, again, link these things to where we want to go to, I want to discuss where we stand with amplitudes, just briefly, or at least to discuss one approach to computing amplitudes and see where these aspects that I will mention fit in. Okay, so recently we have seen that going to or computing complex amplitudes, at least in particular multi-particle amplitudes, is analytically very challenging, and there have been numerical approaches or mixed numerical and analytical approaches to do that. So there is a new, there are lots of tools being developed in the recent years, and you can see a list of some of the authors on the right-hand side. Okay, so let's see what this amplitude computation amounts to. So there's, you see this list in front of you. Unfortunately, I cannot point to items, but there are many steps required in this computation. So the computations typically start with the parameterization of the amplitude integrand in terms of surface terms and cluster integrals. If we have such a parameterization, one continues to discuss, or one uses generalized unitarity and numerical evaluation to determine coefficients in this parameterization. Another important step when doing these things, in particular when switching to numeric, is to set up the computation to be compatible with numerical evaluations. So this is in particular problematic in dimensional regularization. So one needs a numerical formulation of various items that go into this computation. In particular, one needs to know how to deal, for example, with fermions or various other states numerically. So where one can keep the dimension parameter in an analytic form. Okay, a next step is then to recover the analytic dependence on D. So there's a analytic reconstruction step. So one samples over multiple discrete values of D in order to reconstruct the analytic form of D. An important next step is then to replace. So at this stage, one has computed integral coefficients, and one then multiplies in a function basis in its epsilon x function. One cleans up these things, so one extracts the relevant piece, the finite remainder, and if one wants, one can at that stage then try to analytically reconstruct the analytic form of the coefficients. So that's again using multiple numerical samples in order to reconstruct a rational form of coefficients. And finally, one tries to clean up these expressions. And one way to clean up expressions is using Lennart's partial fraction decomposition methods. Okay, so there's lots of steps that we developed or learned how to handle, and there are a few steps I think which are particularly come to mind when thinking elliptic integrals. So I think the one step is the very last one. So if you want to go back to the analytic form of coefficients, it's important to use a good basis for the master integrals. If we do that, then the form of the coefficients is simple or simpler. So I think an important question is always what's a basis of integrals? We know this for what a good basis for integrals, how it is defined for non-elliptic integrals. It will probably be important to find the similar understanding for the elliptic integrals. Okay, so we need a good basis if we want to extend these methods for elliptic cases. Okay, so then there are two places here where vector fields are of importance, and the first place is finding the parameterization of the amplitude, so the very first thing. And then it turns out the next step, there's a second place, and that's actually the numerical evaluation. So generalized unitarity and numerical evaluation. So that's a place where vector fields play a particular role. And we will see that the role they play there is they teach us a bit about the integrands, and maybe that's also linked to finding actually particular forms of the integrands or nice forms of the integrands. So that's in this way, vector fields feed back into finding good forms, or maybe also good forms of integrals. Okay. Okay, so the central object that's relevant for these steps are cut surfaces. So what I mean with this is I want to consider Feynman integrals in momentum space. And I want to consider Feynman integrals modulo pinches. And so if you consider them modulo pinches, this is equivalent to saying that we consider insertions, so tensor insertions, as you see in this equation, modulo terms that depend explicitly on propagator variables. So first of all, so two things get introduced here. So first of all, you have the propagators, or the set of propagators. This set of propagators, they form algebraically, they form an ideal. And we can also associate to this set of propagators a surface, meaning that if we set all these propagators to 0, then we get an algebraic variety. So it's this surface, this algebraic variety that I want to call cut surface. So you see at the same time the algebraic and the geometric picture of this variety here. So one thing is discussing things modulo pinches, and the other thing is setting these propagators to 0. The name cut surface is there just because setting propagators to 0, we usually do this when we study generalized unitarity or unitarity cuts. It makes sense. So these surfaces are actually the surfaces that we usually parameterize when we do unitarity cuts. Okay, so the natural functions to discuss on these surfaces are then given by polynomials modulo propagators, and these are then these simply function rings that one gets by quotienting by propagators, polynomials by propagators. Okay, so there is a particular set of coordinates that's useful when discussing these cut surfaces, and these are the well-known Bykov coordinates, or maybe Katkowski coordinates. Katkowski, I think, introduced them already much earlier, and maybe didn't go as far as Bykov. In any case, what one does in these parameterizations, one replaces the loop momentum by propagator variables plus additional variables that are just required to cover all the dependencies. Here, the propagator variables are called rho, as we've seen already before, and the additional variables, the irreducible scalar products, are called alpha throughout this presentation. Okay, so doing this coordinate transformation, we then arrive at this form of the integral. So the integral is given as a measure in terms of these propagator variables and the ISPs. And then there's this expression where you still see the tensor insertion T. You see the propagators in the denominator, and then you see this Jacobian factor, the B to the power D. So this is the so-called Bykov polynomial, and it's given as a gram determinant of a gram matrix, as written a bit further below. Okay, so this is a convenient way to write the integral, because now rho is really is not a polynomial function, but it's really a variable, so it's very easy to mod out by rho. And discuss actually the on-shell properties. Okay, so one so going to the on-shell properties maybe at the integral level, one can also do by just taking residues now in the variables, and this sets the rho dependence in the insertion and the Bykov polynomial just simply to 0, and we get a simplified integral here. So maybe a word about the interpretation of the objects here. So B is the Jacobian, but we can also imagine it to be associated to the volume of an internal manifold, which is fibered over the space parameterized by the propagator variables and the ISPs. So you can think of just a coordinate space rho alpha, and over each point of this space, imagine a sphere. If you think 2 loops or 1 loop, then you can think there's a sphere sitting on top of this, and the volume of the sphere is essentially given by the value of B. B, being a gram determinant, vanishes at well-known locations. So whenever the loop momenter, so if you look at the equation, defining equation for B, whenever the loop momenter are turned to lie into a plane parameterized by the case, or whenever their dependency degenerates to lie in a subspace not the maximal space they could point to, then this determinant will vanish. So in particular, this volume factor then, so if you're in dim reg and you think it of a one loop diagram and one loop integral, then typically loop momentum takes values in d dimensions, but by Lorentz symmetry, you can rotate it down to 5 dimensions. And this ground determinant then vanishes on the location where the loop momentum further degenerates to lie in a 4-dimensional plane. At two loops, a similar thing happens. So at two loops, typically you can rotate the two loop momentum into the 5th and 6th dimension, and then when they degenerate to lie either in 5 dimensions or in 4, then this spike of polynomial vanishes. And if you think about the space, so what happens in this space, you then have these 0 sets of the Bykov polynomial, and that at the same time is the place where this internal space that is fibered over this space vanishes. So you have basically the Bykov determines for you a boundary when this internal space goes to 0. Okay, so this is just helpful consideration. So in particular, if you want to construct interesting subsurfaces of your space, which have no boundaries. Okay, so let me just discuss this maybe more concretely in one example, and this is just one of the points I wanted to bring. So I think this formulation brings a nice geometric picture, and probably it is helpful when trying to understand geometric properties or topological properties like cycles associated to particular integrals. Okay, so this example here is just the famous double box. You see in the middle, you see a picture of the parameter space in terms of ISP variables. So the propagators are on shell. Then you have this parameter space. In this case, it's 2-dimensional because you have 2 ISPs. And then plotted in red. Yeah, so this space has 2 complex dimensions and 4 real dimensions. And the lines that you see in red are now the vanishing locus of the Bykov polynomials. You see these various lines, which are, if you plot it correctly, these are 2 real dimensional things, so 1 complex dimensional lines. Okay, so then if you want to consider cycles in this space, then what you have to do is you have to find areas. So subsets of this space, and you can put, first of all, open space, things that look open in the ISP plane, but end on the places where the Bykov goes to 0. So these are then places where, so over each point of this space, this internal space, but at this vanishing cycles, vanishing surfaces, this internal space goes to 0 and pinches off the surface. So so whenever you have an open surface that, however, ends on the 0 set of the Bykov, you get a closed surface. So a candidate for a good integration cycle theory. Okay, so there's another picture of the same story, which is much older, and people have probably an easier time to deal with, and that's doing the maximal cut in 4 dimensions. So that's the picture that you see on the very right side. So when you do that, then it was found some time ago that the parameter space that you find out is 6 spheres here, which are connected and have some punctures in them. And I think it's very, so this is a picture that's very helpful to think of also, and it's useful to link the 2 things. So in fact, the middle picture, or the red lines that you see in the middle picture are equivalent to these 6 spheres that you see on the right-hand side. So we said that where the Bykov vanishes, you have a dimension drop, and that then, so the dimensionality, dimension drop, and that corresponds then to these 4-dimensional cuts that you see on the very right-hand side. The various intersection points correspond to the points where the spheres touch. So they are some kind of singular points in this vanishing set of the Bykov. Okay, So the correspondence is not totally obvious, but so one has to realize that in the Bikov coordinates, you can of course go back to the physical momenta, and when you do so, one realizes that one has to invert quadratic equations. So the physical momenta are actually a double cover of the Bikov coordinates. So over each point of this plane in the ISP, you have two momenta sitting, and this doubling then takes these 4 lines or these 3 lines that you see in the central picture and make out of these 3 things. You get these 6 spheres eventually. Okay, so I think that's one thing that I want to discuss. So just Bikov coordinates and extracting some geometric understanding from them. And I will now go on and move towards discussing vector fields using this picture somewhat. Okay, so some of the important properties that we will use later of these cut surfaces are, of course, that that when we try to consider master integrals or understand how many master integrals we have in a given topology, we consider total derivative, or first of all, we consider all the polynomials that live on this space, and then we mod out by the total derivatives, and that gives us the set of master integrals. So that's the typical IVP reduction idea. Okay, so we know this, of course. So then, particular properties of the surfaces of spaces that there are actually distinguished subsurfaces here. We've met them already. So these surfaces are given whenever minors of the Gram matrix vanish. So there's a subsurface where the Bikov vanishes, so that reduces the dimension. So this is associated to reducing the dimensionality of the loop momentum. But you can also have minors vanishing, which imply then that the dimensionality is reduced even further. Right? So these are distinguished surfaces, and they are very natural, and one should typically see them in the computation. One should see traces of this structure. Okay, another important property of the Bikov surfaces are its singularities. So the singularities are given by the location where the Bikov vanishes and all its derivatives with respect to the ISP variables vanish. Okay, so these singularities are interesting in the context of computing leading singularities. So when we compute a leading singularity of an integral, we typically look for places for these isolated singular locations. And so understanding these singularities of the Bikov are particularly important. So what happens now in many cases is that the solutions to these equations are not actually points, but they are surfaces themselves. And so it is, I will discuss in a moment now how you actually find isolated singular points starting from the Bikov surface, even in the case where the singular surface seems to be multidimensional. And discussing singular points is of course particularly interesting because we know, at least intuitively, that whenever we have singularities, we go away from ellipticity of the integrals. So we associate this typically to cycles vanishing, or maybe maybe consequently also intersection numbers to simplify. So that's why discussing singularities is also important. One must say, however, that apart from this topological information, it is not so clear how this simplification actually, what's the mechanism of these simplifications that one observes whenever singularities are around. So in fact, one sees simplification also in the IVP reduction, and it's not totally obvious why this is the case. Okay, so I hope we will discuss this, however, in a bit. Okay, so the first thing I wanted to mention now is this idea of maximal singularities. So we discussed already before the singular surface. So in many cases, so finding the singular surface is just is written, it's just given by the zero set. So one first of all looks for the zero set of the Bykov, and then its derivatives. So in particular, so formulated geometrically, one looks for the places where the rank of the differential of the defining equation of the surface actually drops. So where the rank is 0 in the case that that you see up here. These singularities are typically degenerate. In particular, if you look at the form of the Bykov, then the Bykov is quadratic in these mean variables. So also the derivatives are then linear in the mu variables, and if you have and then setting the mu's to 0 typically solves this with your singular surface, and setting mu to 0, as I mentioned before, corresponds to 0 pushes, so talking two loops, setting the Bykov to 0 pushes the 6-dimensional loop momentum into 5 dimensions, putting the mu's to 0 pushes the loop momentum further down into 4 dimensions. So of course, having 4-dimensional configurations of loop momentum which solve the cut conditions are easy to find typically. So one typically finds degenerate singular surfaces. So one can now, however, continue or extend, then apply it recursively, and that's also something that's well known in mathematics. So, for example, you can find this procedure in Arnold's and et al. Book. So, what you do is you take the ideal that defines your singular surface, and you consider the differential of this ideal, and again you discuss the rank, the location that this rank drops, and this will define for you another variety. And applying this step recursively, you will eventually hit the place where you find discrete and singular points, or maximal singular loci of maximal codimension. In a vector field discussion in a moment. Okay, so let's switch to vector fields now. So the interesting, or the motivations for discussing, or the obvious motivation for discussing vector fields is now, first of all, IUP relations. So the IUP reduction, if you derive IUP relations, you take a total derivative and what you stick in there. So you see the equation, the first equation there, you have a vector field, and then you take a divergence of this. So that's where a vector field shows up. There's another interesting thing that you can do with vector fields. So you can naturally construct D-log forms using vector fields. And this, if you construct these D-log forms, they compute certain indices for associated two vector fields. So they compute something about the critical point, the vanishing points of the vector field. So it would be interesting to see if these D-log forms associated to particular vector fields can actually be exploited for understanding integrals in a better way. And finally, vector fields are interesting because they link to topological information of the underlying surface. And so whenever the topology changes, or if you count the zero set of vector fields, then you get information about the topology of the underlying space. And if a cycle vanishing, then the topology changes, and then you also expect vector fields or new vector fields that have a new set of critical points. So there's through vector fields one should, so if you find new vectors, you get new IUP relations, and then you have a mechanism to remove master integrals, which you should lose because the cycle disappears. So vector fields also give you a link between change in topology and changes in your IUP reduction. Okay, so some important properties of vector fields that we discussed. So we will always discuss polynomial vector fields. And these vector fields you have written up there, so they can be parameterized in terms of all the vectors that you have in your problems, the loop momentum vectors and the external momentum K, loop momentum vectors L. And this particular form implies that whenever the loop momentum, when you move to a place in loop momentum space where the dimensionality of L changes from D to a lower dimension, then also the dimensionality or the direction the vector field points to will also change. So if you go to a place where the loop momentum points, let's say in 5 dimensions, then the vector field will also point in 5 dimensions. If you go to a place where the loop momentum is 4-dimensional, then the vector field will point into 4 dimensions. So this means that the vector fields themselves, they are actually tangent vectors to the surfaces defined by the minors of the graph matrices. And so in particular, and in formulas, you see this below. So a vector field acting on a Bykov gives something that is vanishing at the locus of where the Bykov vanishes. So you have a vector field acting on the Bykov, which gives back the Bykov. Vector field acting on mu variables, which are minors of the ground matrix, should return again expressions in the mu variables. So these are interesting properties. So they are also tangent to these distinguished surfaces, that we discussed earlier, and yeah. Okay, so then there's another way to see these relations show up, and that's when we discuss IUP relations in Bykov coordinates. Okay. All right. So there are now particular vectors. So these are generic vector fields, polynomial vector fields, but they are vector fields associated to a given topology, and these were introduced by Glutakaida and Kosover some time ago. So they are vector fields which are actually tangent to the cut surfaces. So the derivatives acting on a propagator returns again a propagator. So then this this implies that these vectors are actually in the kernel of the differential of the propagators when you go to the surface where the propagators are 0. So these were introduced initially as particular vectors that you can use for generating IP relations that do not double propagators. However, they have, of course, this geometric meaning that they are tangent to the cut surface. And in fact, their geometric meaning is even a bit stronger than that. So they're not only tangent to the cut surface, but they're also tangent to the cut surface and all its pinches. So in particular, the right-hand side depends on so the index of the propagator on the right-hand side and the left-hand side is the same, and which doesn't need to be the case for tangent vectors. But in this way, they so this is a bit of a stronger condition than for tangent vectors only. Okay, so it's interesting to discuss now these vector fields in the Bykov coordinates. So so you see here the change of coordinates to Bykov coordinates. Again, in Bykov coordinates, you then have a sum of so you have, again, this defining equation of these tangent vectors written up there. It can be solved explicitly. And yeah, so it turns out that if you're in this Bykov coordinates, it's very easy to solve this defining equation for tangentiality with respect to propagator variables. However, what is when you start with a vector like this, usually you lose the condition that these vector fields should be tangent also to surfaces of lower dimension, and that's then a second equation that you have to add in, and that's the second equation you find here. It's for us, it will be important only to consider these vector fields on shell. So, and the last equation that you find is now the equation, the way the tangentiality equation looks for on shell. So you have a derivative acting on a Bikov should return the Bikov as the equation. These kind of equations, yeah, they are so-called syzygy equations, and they can be solved by computational algebraic geometry in a quite efficient way. Okay, so there are various types of these vectors. So one can, actually vectors you can write down explicitly, so-called generic vectors, and they can be written down by, where you see these vectors VG and VB, and can just written down by inspection. So just by taking the equation and symmetrizing in the right way, then you find these first two vectors. And yeah, you can always find them no matter what the form of the Bikov is. And then if the Bikov surface is singular, you typically find additional, or you can find additional vectors. So non-trivial syzygies. Okay, so there one sees that whenever you have singularity, something new is kicking in. Okay, so the simplest example here is the one loop examples. On the left-hand side, you see a massless triangle. The Bikov is here just given by alpha 1 squared, alpha 2 squared. The generic vectors are just rotation generators. And this VP vector, which we are maybe less familiar with. And then finally, this particular vector is this so-called scaling vector, which really amounts to a conformal transformation. So this is VS, which has the components alpha 1, alpha 2, and 2. And this amounts to a conformal transformation. So the Bikov, the vanishing set of the Bikov is really a cone, and then there's a conformal transformation that leaves this cone invariant. And the three-mass triangle you see on the right-hand side, there the Bikov is changed. So it has actually this constant C sitting there, and you do not have this. So this is a regular surface. You don't get the non-trivial syzygy relations, and you only get these rotation generators and the other vector. Okay, so this is just to get a feeling for what things are. So non-trivial syzygies are always something like scaling transformation locally around the singularities of the Bikov surface. Okay, so it's interesting to study actually the components of these vector fields in some more detail now. And so we have now, the components of the syzygy solution. Let's say this. So they are the V's. So if you go to the last equation here, there are the V's, and then there's the F. So all these things together, they form a syzygy. And here, well, the equation is written here again. So you have these V's multiplying the derivatives of the Bikov, and then you have one term which is F and times B. So this equation we want to solve, or tangent vectors solve this equation. And now we can discuss this on particular surfaces of the particular places of the cut surface. So in particular, we can look at the extremers. So if you look at an extremum of the Bikov, then the Bikov itself is non-vanishing. So an extremum that's not a singularity, then the Bikov is non-vanishing, but the derivatives of the Bikov are vanishing. So for this equation to hold, you need that this f of b actually vanishes. Okay, so whenever you have a syzygy solution on the extremer, f of b vanishes. Then you have a second place, which is interesting. So these are the singularities. The singularities of the Bikov. The Bikov itself vanishes, and the derivative of the Bikov vanishes. And because the derivative vanishes, the Bikov itself vanishes quadratically. So if you again put this into that equation, then one finds the VI's have to vanish at the singularities, but the FB's typically do not vanish at the singularities. Okay, so one can now take these observations and play with them. And what one finds is that we can now use the components of the vectors to discuss some of the properties of the cut surface. So if you look for the place where, so if you compute all the vectors and you look for the place where the FB's of all these vectors vanish, then the set of solutions corresponds exactly the number of extrema of the Bykov extrema, which are not singularities at the same time. And these numbers actually correspond to the number of master integrals. So if you so you can, without doing an IUP reduction, you can just compute these vectors, and for the vectors you can read out the number of master integrals rather straightforward. Another thing that you can do with the vectors is if you look at the V components. So if you set the V components to 0 of all your vectors, then what you get is the maximal codimension singularities of the Bykov surface. So instead of doing an analysis with minors, you can just set these things to 0 and find the singularities rather quickly. You can also turn it around. So if you know what the singularities are, you know a lot already about the vectors, and you can also make their construction simpler. Okay, so another thing that you can do now that you notice, we can calculate actually surface terms using these vectors, and then we can also discuss their properties. So here I wrote down the surface terms for these 3 types of vectors. And what one observes is that these surface terms, they vanish on particular surfaces as well. So on the extremer, the first type of surface terms, so this mg, vanishes. On the singularities, the first 2 vanish. And also the last surface and last type of surface terms vanishes on the singularities, provided the p vanishes. These polynomials p vanish on the singularities. Okay, so we find interesting surfaces where these surface terms vanish. That's actually quite helpful for the IUP reduction. So IUP reduction, just written down quickly here on shell, is the following. So we have a tensor insertion, the T of alpha, and it gets equated with the number of surface terms and the number of master integrals with a priori 3 coefficients. And the IUP reduction amounts to computing these coefficients. And one way to solve these equations, so these linear equations for the coefficient, is to evaluate this equation on multiple points. So for the ISP variables alpha, and yeah, so you can do this numerically. And of course, what determines how easy it is to solve this equation is the number of surface terms, or the number of surface terms, or also the number of values of alpha that you have to insert. So what you can do now is you can actually remember that the surface terms vanish at particular places, and you can actually sample these kind of locations. And by this, you reduce the linear system, and you can simplify these computations. You can even go one step further. You can try to understand these distinguished locations even better, and try to line up actually your master integrals with respect to these distinguished surfaces. And yeah, so I believe that will actually lead to understanding better what are good and less good forms for the expressions for master integrals. Okay, so I collected a little bit of information here on how to do that. So you can actually use this information about the singularities to write your expressions in a particular basis. So actually express your tensor insertions in terms of the polynomials that vanish on the singularities, for example, or on the extremer. And you can build up some sort of Taylor expansions of that sort. And I think you can use these expansions to solve the IUP systems more efficiently. But maybe one can even see structures to find explicit solutions to these systems in that way. So I noted here to diagonalize the IUP system. Okay, I was very short here because I think I'm out of time already. So I'm trying to conclude. So discussed vector fields, which are a natural structure associated to Feynman integrals. So there's the cut surface, and then these are properties of the cut surface, so they naturally appear. We have seen that properties of the vector fields actually have an imprint on the IPP reduction. We can find interesting probably we can use these vector fields also to learn quite a bit about the integrals themselves. So there are these maximal codimension singularities, and I find them very intriguing for discussing leading singularities. And we've seen also this one example where you can use the zeros of the vector fields to count master integrals. So I think it will be interesting to see if there are further things that we can actually learn from the vector fields about the topology. And yeah, finally, of course, for amplitude computations, we need vector fields. So learning about them and finding better ways to get these vector fields will actually also help on that side. Okay, so that's all. Thanks for now.
Thanks, Harald, for such a nice talk. Let's take 2 seconds to unmute ourselves and give Harald a round of applause. So if anyone has any questions, yeah, okay, I see already a question from Roman Lee. Please go ahead, Roman.
Hi, Harald.
Hi.
I want to ask you, you said that there is some similar features of your approach with the one that we used with Andrei Pomeransky in our paper to count master integrals. I just want to understand, is it interpretation which is different, or technically it is you do something different to count the master integrals? Because we also used, both Feynman parameterization and Bykov parameterization, and it seems that for Bykov parameterization, you can probably do the only thing that we did.
Yeah, well, I would think it's the same. So nothing new, apart maybe from the fact that it didn't dig into the singularities that much. I think you found the singularities and then maybe you decomposed your solutions, but you didn't. I think you could have gone one step further in discussing degenerate singular surfaces. Also, in the Bykov representation. But
yeah, connected to this, I would also want to ask a question about, singularities at infinity, or critical points at infinity, because you know that. For example, MINT, it gives sometimes less master integrals than there are in this sector, and we do believe, and actually we checked in several examples, that it is connected to the phenomenon of critical points at infinity, which means which comes because we we have to compactify somehow our space, so we don't know how to do it in a proper way.
Yeah.
In particular, how to use commutative algebra to.
Yeah. Well, I must say I'm too experimental, too phenomenological in the moment, so I cannot say anything about this. It would be interesting to have an example actually where this problem appears in the Bykov representation.
Yeah,
to try it.
It seems to appear simultaneously. So
it's
if it appears
same,
in Feynman representation, it appears also in Bykov representation. Unfortunately, you cannot get the right answer in both of them. So I can give you.
Yeah, if you have something, would be great. Yeah.
Yeah. Okay.
Okay. Yeah. Thanks.
If anyone else has questions, please raise your hands. I have a very general question actually about this good functional basis. So what do you think is you didn't talk much about what can be considered good functional basis for elliptic integrals. In particular, for example, this pure functions for elliptic multiple polylogarithm, can they be considered a good functional basis for amplitude computation, for instance? Do you have anything to talk about it? Do you have any comments?
Well, I don't have any experience with that.
Okay.
I mean, I don't know of an explicit, at least we have not done an explicit computation where this kind of simplification showed up.
Okay.
Just because we didn't do it. I think the right people to ask is probably the ones that consider the IUP reduction with including elliptic integrals. So I think there should be a lot of experience here. For example, looking at yeah.
Yeah, we can also discuss tomorrow during discussions about this. I see another question from Matthias Falk. Matthias, please go ahead.
Yes, thanks. So I have a question about what you mean by this left elliptic that you said. So does it mean that you start with some, I don't know, high dimensional space and you see it degenerate somehow, or is it more meant in the sense that when you reduce to master integrals, you get less that have some elliptic structure, or what do you mean by this?
Yeah. For me, you're asking me, right?
No, well,
okay.
I don't know. Well, if you have the answer, yeah. Sure.
No, I thought you were asking about my question. Sorry, sorry, that was for Harald.
No, it doesn't matter who answers the question.
No.
So what you refer to the point where it said where it says the more singular the less elliptic, or is that?
Yeah, exactly. Yeah.
Well, I think about the torus, for example. If you have a torus, you have two cycles and they intersect, and this intersection is sort of the critical issue that can lead to elliptic integrals. However, if you pinch the torus so that it decomposes into two spheres that they touch each other at points, then you lose the ellipticity. Particularly, you lose cycle and you lose also intersection numbers. In this sense, if you have singularities, something breaks, and it breaks in a good way, I think.
Okay, but so it's really meant like literally for an elliptic case, and you see the elliptic curve disappear in some sense, or
just elliptic. I think you can, in many cases, you can probably kill intersection numbers if you make certain cycles shrink, right? Or
okay,
vanish. Yeah. And that typically leads to singularities.
Okay, thanks.
Okay, so since we are already out of time, I want to let's thank Harald again. Okay, so the next speaker for today is Robin Marzucca from Durham. He will talk about numerical evaluation of elliptic polylogarithms. So without further ado, please go ahead. I'll switch off my.
Yes, thank you. Thank you to the organizers for setting up this conference and also for inviting me to present my recent work here. So today, again, we're going to talk about numerical evaluation of elliptic polylogs. And for me, the motivation is exactly the same, namely that and despite all the, we have made a lot of great progress in terms of Feynman integrals that contain elliptic sectors. But at the end of the day, at some point, we do want to get numbers out of those in order to do some phenomenological studies. And for this, we need a way to extract these numbers, and ideally, this will be an efficient algorithm. So let me just briefly set the stage. So these are the elliptic polylogs I will be talking about. So these gamma tilde functions, which most of you have seen many times before, already this week and before as well, probably. And they're defined as iterated integrals over these functions Gn. And these functions Gn, they are the expansion coefficients of the Kronecker-Eisenstein series F, which is seen here, which is defined as a ratio of Jacobi theta functions. And the Jacobi theta functions, we've heard this already yesterday from Stefan. There are many conventions, different conventions for these, and this is the one we used, although I believe it probably doesn't really matter too much. Anyway, so we see here already that so we have this sign of 2n plus 1 pi z. So this f is periodic in z, obviously, and if you take the ratio, you'll find that it is also quasi-periodic in shifts in tau, which means that if you shift your argument z by tau, you'll get this exponential e to the minus 2 pi I alpha multiplying the Kronecker-Eisenstein series evaluated at z. And of course, these properties translate also to the expansion coefficients. so to these GNs, meaning that again, this Gn of Z plus 1 is equal to Gn of Z, and Gn of Z plus tau, you can get, you can essentially get a shift where you get a sum of different of these expansion coefficients. Okay, now, as I said, many computations have been done in the literature using elliptic polylogs. And in cases where they depend only on tau, there are actually means to get a number out of them, which is that you can transform them to iterated integrals of modular forms, which you can then Q expand. And then this Q expansion you can evaluate numerically. And this has been done by many people before, and I've certainly not managed to find all of them, so there's some few dots here. And our goal is to in the end, to find something similar for elliptic polylogs. First, I'll go a little bit into modular forms. So modular form is essentially a function that behaves nicely under these modular transformations, so transformations in SL2Z. And when I say behaves nicely, what I mean is the following. So a modular form f of weight n is, first of all, is a holomorphic function. It is holomorphic as tau goes to I infinity, and it behaves in the following way under modular transformations. So you get this factor c tau plus d to the power of n, and this n here is the weight of the modular form. And then they are related to the elliptic integrals that I'm considering, namely if you have an EMPL evaluated at a rational point. And by this I mean that the argument z and all the zi's, they are of the form a plus b tau, where a and b are rational numbers. And in this, if we have an EMPL of this form, then we can rewrite it in terms of iterated Eisenstein integrals. And we can do this using the coaction, and I'll be very brief here because this will not be the main topic of my talk. Obviously, if two functions are the same, then their coaction must be the same either. And the coaction of an elliptic multiple polylog can be cast in this form, so you get a sum over tensor products, the first entry of which can be written again as an elliptic multiple polylogarithm, and the second entry can be cast as a word of one forms, and in particular one forms that contain this Kronecker Eisenstein coefficient. Right, so if we want to rewrite this in terms of iterated Eisenstein integrals, we'll notice that, and this is where the rational points come in, these Kronecker Eisenstein coefficients can be written in terms of these functions h, which are the Eisenstein series. And these are modular forms, okay? So then what you'll have to do is you take the coproduct of an EMPL and you apply this function which extracts the cusp value at I infinity from the first factor and integrates the word of one form. So you get an iterated integral, which is exactly an iterated integral of Eisenstein series in this case. And these functions, they can be evaluated numerically by computing the Q expansion. And this has been done many times before. And now we're gonna have a look at how we can do something similar just on elliptic multiple polylogarithms. So let's come to this. First of all, so our goal is to find a series expansion of an EMPL that has three properties. First of all, it should be well defined. Second of all, the convergence should be quick because we may want to evaluate this to high precisions. And then lastly, obviously, we also want to be able to evaluate the expansion coefficients. Otherwise, all of this is no use. So these are the types of elliptic polylogs we're going to look at from now on. So the integral from 0 to z will always consider the straight line. And we want all the EMPLs that we consider to be well defined. Now, what I mean by that is the following. So you know that these Kronecker-Eisenstein coefficients, they can have poles at these lattice points of the lattice defined by tau. For n larger than 1, there's no poles on the real axis, but for n equals to 1, you can also find poles on the real axis. And when we say the elliptic multiple polylog should be well defined, that means that we only consider EMPLs where Z is such that there are no poles between 0 and Z, so on the straight line between 0 and Z. First of all, obviously, if the endpoint is on a pole, then the integral diverges. And second of all, if you have a pole somewhere in the middle on this line, you can regularize this by integrating around the pole, but then of course, depending on which way you deform the contour, you will get different values. So this is something that the user will have to deal with beforehand. Okay, now these coefficients, G, they can be formally expanded as a Q series, where Q is defined as e to the 2 pi I tau. And the expansion looks something like this, which you may or may not have seen before, but you probably have. And of course, if tau is in the upper half plane, if the imaginary part of tau is larger than 0, that means that the modulus of Q is smaller than 1, which in turn means, well, which is a good sign for this thing to converge. However, we also have this dependence on Z here, which is also a complex number. So we'll have to be a little more careful, so, because the convergence of this series also depends on the value Z. So the first thing, right, so if we consider this recursion for the elliptic multiple polylogarithm, we have this integral over Z prime of G of Z prime minus Z1. So this must mean that these the series expansion of the Q series of these G's must converge on the whole range from 0 to Z on the whole straight line. And then we can go and perform the expansion and then do the integration afterwards. So the first step of our algorithm is to prepare the elliptic multiple polylogarithm. So first of all, this is the easiest step. We want to use the quasi-periodicity of these Kronecker-Eisenstein coefficients to shift all the Zi to the fundamental domain, which we call it, which is not to be confused with the fundamental domain of SL2Z, which is just defined by this fundamental parallelogram. Okay, so this is straightforward. So we have a little example. Here, let's assume Z1 is already in this in d tau. Then here we can shift the integer values just for free, essentially. And then when we shift this tau, we get the quasi-periodicity kicks in, and we get a term, a sum of two terms, first of which has a 2 pi I here. Okay, so that was step one. Now, step two is to regularize the EMPLs, which have 1, 0 as their last argument in here, because of course these will formally diverge. They have a singularity at z equals to 0, so at the starting point of the integration, which we don't want. So, and we've also seen this in talks before, so we can regularize these EMPLs using shuffle relations, which means that we can write them as a polynomial in these gamma tilde 1, 0 z tau, where all the coefficients of this polynomial are finite and well defined for z equal to tau. Again, so I've picked the example, this gamma tilde, which we've, and the gamma tilde 1, 0 z tau, you can regularize, well, in principle, as you like. So we chose this form here. I believe we've seen a different form in a talk yesterday. And here's the example. So this is the EMPL we saw in the previous example, which has a 1, 0 here in the back. So you can use shuffle relations to write it in this form. And now all of these EMPLs are regularized and finite for z going to 0. Okay, so At this point, all of our EMPLs are well defined, and we can start to think about the convergence of the Q series. But it is very important to first regularize them before the next step, because otherwise you might get some wrong results. So step 3 is to optimize the convergence. What does that mean? So as we've seen before, the convergence of the Q series depends on this modulus of Q. And at least since tau is in the upper half plane, we have that Q is much smaller than, that the modulus of Q is much smaller than 1, and depends on this imaginary part of tau. However, if you just, I mean, being in the upper half plane doesn't mean too much, because the imaginary part of tau can in principle become as small as it wants. So luckily, we can use modular transformations to shift any tau in the upper half plane into the fundamental domain of SL2C, which is this shaded area up here, which continues on to I infinity. And of course, once you've done this, then the smallest imaginary part you can possibly get is here at this edge down here. So imaginary part of tau will always be at least square root of 3/2, which means that the modulus of Q will be smaller than 0.004, roughly. So this is very good for the convergence of the Q series. Now, this is step 3, so we optimize tau, which means we map it to the fundamental domain. And to do this, we have to use the properties again of these Kronecker Eisenstein coefficients. So under modular transformations, they transform, as you can see here. And we can use this to take an EMPL evaluated at a tau which is not in the fundamental domain and rewrite it as an EMPL which is in the fundamental domain. So you have a simple example again, because these things can get quite messy, but so we have let's assume that tau is in the fundamental domain, then obviously -1/tau is not. So and then we can rewrite this EMPL as a linear combination of these two terms. Okay, very good. So now we've got something which in principle will converge quickly. However, the step 3, so the mapping to the fundamental domain, does not necessarily commute with the first 2 steps that we've taken, which means that at this point, we'll have to start again at step 1 and go through these 2 steps again. This is, however, not too much of a problem because these steps are usually pretty quick. Okay, once we've done that, we come to step 4, which is to prepare the argument Z, so the upper integration boundary. And in particular, we want Z to be in this, well, half of the fundamental domain d tau, we call this d tau prime. And this can be easily done as well. So first of all, if Z lies in the lower half plane, then we can use reflection identities of these G's. So we can use parity to rewrite the EMPL as an EMPL of -Z. So then Z is somewhere in the upper half plane. And then we can use path decomposition to split this path, this integration path, along, for example, the intersection points with the lattice defined by tau, and then shift all the integrations, and then shift all the EMPLs that we get from this path decomposition, such that they're again defined as integrals from 0 to psi I plus 1 minus psi I. Okay, and again, I have a little example. So this EMPL N1Z1Z can be, we can decompose the path such that we have an integral from 0 to psi 1 and an integral from 0 to Z minus psi 1, where again, we have shifted the argument Z1 here as well when redefining the integration. And of course, then now this Z1 minus psi 1 does not necessarily lie in this in the fundamental domain d tau anymore. So for the very last time, we'll have to go back to step 1. Okay, now once we're through the first steps again, we finally have an expression in terms of elliptic polylogs that are ripe to be expanded. So this is step 5. We're going to compute the Q series. Okay, so we have an expression in terms of EMPLs which are well defined and where the Q expansion converges on the whole path of integration. So this means that we can now expand the integrand and then integrate the different coefficients of the expansion separately. Now, what do these coefficients look like? Obviously, they're also going to be iterated integrals, and they're going to be iterated integrals of this form. So we have this function f here, which consists of these terms. So these trigonometric functions, which are exactly the functions we've seen in the Q expansion of the Kronecker-Eisenstein coefficients. Now, in order to perform these integrations, what we want to do is we want to change variables from these sigma i's to psi I to chi I, which is defined as e to the 2 pi I sigma I, and we're going to call e to the 2 pi I zi wi, and e to the 2 pi I z we're going to call w. What we get is an iterated integral, this time from 1 to w of some function g, where now the function is a product of terms of this form. And now, of course, these are rational functions, right? So we know that these iterated integrals will evaluate to regular multiple polylogarithms. So this is good because obviously we want a Q expansion that we can evaluate afterwards. So, and from now on, I'm gonna talk a bit about this transformation. I'm gonna call this everything that happens here Z space, and everything that happens here I'm gonna call W space. So yes, we get multiple polylogarithms. So there's one more subtlety in this step, which is however crucial. So we switch from this integration in Z space from 0 to Z to an integration in W space going from 1 to W. However, the integrals, they can have logarithmic branch cuts, right? So we can have simple poles in the integrand. So what happens is in Z space, we have this integration on this straight line, which in W space gets mapped to this blue curve here. And this pole Z1 here gets mapped to this pole W1. So clearly we can't just integrate on the straight line path in W space, because then we would pick up a residue here that we need to consider. Now we can solve this problem by doing the following. If we take these poles Z1 and Z2 and draw these blue lines, which are just parallel to the imaginary axis, and then we compute these intersection points Z tilde of the original integration path with the blue lines, then all of this is mapped in W space to this curve. And if we integrate along this orange line here, so to W1 tilde and W2 tilde and then to W, we ensure that we're always crossing the path on the correct side of this pole, because these blue lines get mapped to essentially the angles under which we find the pole, and this way we are always on the correct side of the pole on a specific angle. Okay, very good. So now we've got an algorithm that can do that we can use to expand elliptic polylogs, and now we come to some applications of this. One of the applications is the banana diagram, which has been considered by quite a lot of people already as well. I think some of which are here in the audience. And in particular, we're going to consider the equal mass case of the banana diagram. So this corresponds to an integral family defined here. So we get the A1 to A4 are the exponents of the 4 propagators, and we want to integrate this over 3 loop momenta. And this integral family has well, 3 master integrals, 4 if you count the tadpole, which we can normalize to 1. And these are the 4 master integrals we chose in our paper when we computed these integrals. And we defined x to be the ratio minus 4m squared over p squared. And since all 3 of these integrals are finite in 2 dimensions, we are going to consider these integrals in epsilon, for epsilon equal to 0. And we have computed these integrals first in terms of iterated Eisenstein integrals, or iterated integrals of modular forms, which we have then transformed to an expression in terms of elliptic multiple polylogarithms using the algorithm that I described before. And now I went and took the expression of the master integrals that we obtained in terms of elliptic polylogs and evaluated it numerically using the algorithm that I just described. And so for one, we evaluated it for some ratio minus p squared over m squared equals to 100. And I computed the first 100 digits. Well, I'm showing you the first 100 digits of the 3 master integrals at this value, which of course we could cross-check using the expression in terms of iterated Eisenstein integrals that we had. Yeah, so this worked pretty nicely. Then I also went and made some plots for the 3 master integrals, which are horribly labeled. Okay, so this is the integral I1, this is I2, and this is I3. And I plotted them from minus p squared over m squared from 0.1 to 1000. Okay, so actually I plotted the inverse, as you can see, but this is what they look like. And in order to make these plots, actually, I used a property of the output of our algorithm, which is quite nice, namely that you can compute an expansion and reuse it to a certain degree. So in principle, you can do this expansion up to the path decomposition of along these orange line bits. And as long as that remains in this fundamental domain d tau, you can actually reuse your expansion as many times as you want. So I actually only had to compute 1 expansion, and then just I was able to make the whole plots here. So this is obviously very nice if you want to evaluate your result at multiple phase space points. And then lastly, now I want to go back to this relation between EMPLs at rational points and iterated integrals of modular forms. So to write an elliptic multiple polylogarithm at rational points as an integral of modular forms, I've showed you before, you have to apply this map, which computes the cusp value of the first entry, which is an elliptic multiple polylog, and integrates the second one. And of course, the cusp value at I infinity corresponds to the leading term of the Q expansion that we're computing. So that's another, I think, quite useful application of our algorithm. Yeah, so this would be the algorithm. We've found a Q expansion of EMPLs. The algorithm, or the convergence of the algorithm, is optimized to some degree at least. I don't know if there's any other things you can play there, but at least mapping tau to the fundamental domain optimizes the convergence in some way. We get coefficients which can be cast in terms of multiple polylogs, so we can evaluate these coefficients. And so far we have implemented the algorithm in Mathematica, and we're planning to, or we have started to implement it also in C++ to make the whole thing even a little faster. And yes, I guess I was a little fast, but this will be it. Thank you.
Thank you, Robin. Let's take 2 seconds to unmute ourselves and give a huge round of applause for Robin. So I see a few questions from the audience. Lorenzo?
Yes, hi, Robin.
Hey.
So I have a quick question, probably I just maybe missed something, but if you go to slide 37 where you showed the numerical evaluation, so is there a reason why you're not going above threshold? So there's no imaginary part here, you're only showing the real part.
Yes, I just, I was busy the last days and I didn't want to bother with doing the analytic continuation.
But it is possible, right? So there is no reason why you're not showing it here. Yeah,
no, of course you can.
Yeah, okay, thank you.
David?
Yes, my question is closely related to Lorenzo's. I point out that the original calculation by Bloch and Van Hove chose the modular parameterization so that tau I infinity, q equals 0, was actually at the branch point. They expanded about the branch point. And in general, I think that we should be thinking of doing calculations, you know, in Minkowski space, not in safe regimes where the amplitudes we're dealing with can have imaginary parts. And I wonder if your program can handle that.
Well, I mean, the program can essentially, I would say, handle any well-defined gamma tilde that you give us. Right.
So, for instance, on the top lip of the cut, you could handle it. There would be no problems. We wouldn't have to subscribe our own I epsilon to tell you what Riemann sheet you were on. Well,
that's the thing. So we assume that the integrals are well defined on the path of the integration. So if there's an ambiguity on which Riemann sheet you want to pick, then we have to specify this beforehand in some way. But I'm sure this can be done by preparing the EMP outs accordingly.
Thank you.
Okay, in the time people think about other questions to ask, maybe I have a few quick questions about the speed. In particular, this part decomposition using lattice, how fast, how expensive is it? Is it like, what's the speed of?
I mean, this is essentially instant. So you mean this here,
yeah.
Right? No, this is pretty much instant because you can just, I believe already in Polylog tools, there is essentially an algorithm that does this for polylogs, but not too much changes here for elliptic polylogs. So the expensive step really is the expansion here. For example, maybe I should have, I thought I put down the number here, but so here just doing all the steps 1 through 4 was a matter of seconds on all of the integrals. Mm-hmm. And then the expansion, so I expanded all appearing elliptic polylogs that are in my expression after I regularized them and decomposed the path. So I think they were around 700 EMPLs, and expanding all of them took about 25 minutes. And then evaluating the expression with in terms of polylogs took, I believe, about 10 minutes or so.
Okay, before I ask Stefan to ask his question, there is a comment from Claude.
Yeah, so maybe to comment on David and Lorenzo's question about the analytic continuation. And you can do that. So what is discussed here is just the evaluation of the elliptic polylogs. To analytically continue it, you would have to analytically continue essentially the homogeneous solution, which means tau, which means modular transformation on tau. So you know how the elliptic polylogs transform under modular transformation. You would get a different representation of the elliptic polylogs at a different value of tau, which you map back to the fundamental domain, just what you would do with the modular forms as well. And then in this transformation, you produce the imaginary parts, just like with modular forms. And then the whole thing starts again from there.
Yes, precisely.
So the analytic continuation step is in some sense decoupled from the question, how do you get the numerics if you have mapped all your points to a place where you know that you have a fast convergence series?
Yes, thank you, Claude.
Okay, Stefan, go ahead.
I have just a small question. You mentioned several times go back to step 1.
Yes.
I understand that, but my question is it clear that this procedure terminates always?
Yeah, so once you went back to, so step 1 and 2 essentially only act on the indices Z1 to Zk here and leave Z and tau invariant. So you just have to go back to step once every after step 3 and after step 5, and then afterwards you'll be done.
Okay.
Okay, if there are no more questions, we thank Robin again. Yeah, there's a room on Slack also with numerical evaluation. In case someone wants to ask there, please feel free to put your question there. Now we have a 45 minutes coffee break. Actually, now we have, we resume at 4:15 and see you all there. And I invite Pierpaolo to check his slides during the break.
Thank you.
Okay, so we can resume at 4:15.
Yes, and speaking of, it looks like most people have come back from the coffee break. There might still be a few more trickling in. So for those who didn't hear what was just discussed, the schedule originally had Sebastian Mazzara. It turns out he's a bit under the weather, but Pierpaolo has graciously agreed to give a talk in his place. And so as our first talk after the break today, Pierpaolo Mastrolia will be telling us about the vector space structure of Feynman. You can give it away.
Okay, thank you, the organizer, for the opportunity. As I said, it's really a pity Sebastian cannot be here. I'll try to tell you about a few works that we did together, in particular on the application of intersection theory to the to the structure of Feynman integrals. It's a common work that I started with him, an analysis that I started with him almost a couple of years ago, that we pushed forward thanks to the energetic input of Stefano Laporta, Hjalte Frelleswig, who are here, Manoj Mandal, as well as two PhD students like Federico Gasparotto and Luca Mattiazzi, whom I can really recommend for the next selection application. Particularly, I think Luca is about to finish his PhD, and so I take this occasion really to endorse his application. So this is a program that we started in order to apply the key concept borrowed from intersection theory to study the algebra of Feynman integrals and the algebraic property. We know that scattering amplitudes are important for key ingredient for perturbation theory, but lately my interest has been also focused on finding the connection between Feynman integrals and general relativity in the context of the physics of gravitational waves. And there has been a tremendous progress in this direction in the last couple of years after the discovery of the gravitational waves. And I look forward that the ideas that came from different directions and that are helping our cosmologist friend can also give a hand on improving the techniques and the toolkit that are available for solid-state physicists, in particular to to study the effective field theory approach to hydrodynamics and superfluidity, in particular to the scattering of vortices and emission of sound wave. So let me start from a comment of Schwarz and Shapiro, where they say that physics is a part of mathematics devoted to the calculation of integrals of this form, integral of gx over e to fx in the x. And different branches of physics are distinguished by the name of the variable and the name that we give to these functions. Of course, as they say, this is a joke. Physics is not part of mathematics, but it's out of question that as a physicist, we content ourselves to know what surrounds us up to a total derivative. And as also in many cases in the physics application, it happened, we forget the role of the integration boundary. Also in their formula, there is no integration boundary, but it's understood the property to be there in order to guarantee the vanishing of a total divergences here. So Feynman integral in the most general definition are just in the momentum space representation multivalued multidimensional integrals over generically inverse power of denominators. We can represent them genuine denominators associated to graph as well as irreducible scalar product. And the number of them is really dictated by the external leg, by the external topology of the diagram, and by the internal number of lines. Now, we know that there was we have been witnessing and participated in the development of, in the last decades, of on-shell and unitarity-based methods, which have been developed by people present in the audience. And a few key ingredients were brought into the game by the use of Cauchy residue theorem inside the factorization property of the amplitude. And the idea that special complex integration technique may reveal new property of the amplitude was the key element of this revolution. What happens for tree-level is intimately connected to the loop, in particular the tree-level factorization, inspired a tandem progress on the analysis of the quadruple cut technique, which enable to extract the coefficient of an integral, in particular of the box, one loop box function, essentially by residue theorem. In the same spirit, a while ago, I proposed the use of the double cuts and Stokes theorem to extract the coefficient of the bubble. We also had to use at that time introduce a complex parameterization of the loop momentum and a special twofold integration, which was carried through by two operations. One, calculation of a primitive integral with respect to one of the two variables, either z or z bar. Here in this slide, I'm choosing z bar, and then a complex residue theorem applied to the other variable z. This also allowed to extract the coefficient of the bubble in a suitable way. Already at that time, I've been computing an intersection number, but I admit that I did not know yet. So then the integrand decomposition, together with the unitarity-based method, enabled the striking NLO revolution that we have been having in the last decade, in particular for collider physics. And the analysis of the integrand pushed forward at one loop indeed was generalized to higher number of loop with the classification of the residue and the integrand structure that are sitting on top of the product of denominators. This integrand decomposition has been used in several applications, in particular allowed to reconstruct efficiently the integrand, even in a unitarity-based decomposition, in unitarity-inspired way, by fitting procedure. Now, the integrand decomposition at one loop was extremely successful because the number of individual monomial was limited, but at higher order we knew that there were leftover integrals that do not integrate to zero, and these still characterize the difficulty level, complexity level for the calculation. But in the same spirit as unitarity cut, we proposed the maximum cut theorem, or the generalized cut for box function. We proposed the maximum cut theorem, which is the classification or the determination of the residues for those diagrams for which, when cutting all denominator on the maximal cut, actually the maximal cut would correspond to the freezing of the integral. Okay, exactly like for the quadruple cut. At dual loop, you are left over with no integration variable. Here, the maximum cut is for arbitrary loop is exactly obtained by imposing the vanishing of a given number of denominators that freeze completely loop momenta. And what's nice of this theorem is that borrowing the shape lemma from computational algebraic geometry, we settle an identity between the number of solutions to the cut condition and the number of independent coefficients in the residues. We know that for the one loop quadruple cut, there are two solutions in 4 dimensions, and indeed there are two coefficients in the residues, as well as in the pentagon in the dimension, there is only one solution. One is the number of the coefficient of the residue, and this you can generalize at one loop higher and so on. What's important is that essentially the number of solutions of a zero-dimensional theorem, of a zero-dimensional system, corresponds to the dimension of the quotient ring between the polynomial ring and modulo the generators associated to the ideal corresponding to the denominators. We will see later on how shape lemma enters into the intersection theory game. So Feynman integrals have been successfully introduced in the at the end of the 50s, and a key ingredient was definitely the use of dimensional regularization, out of which, as a byproduct, the integration by parts identities over the last 40 years have characterized an important toolkit to access calculation beyond one loop. In a different representation, in a parametric representation upon changing of variable from momentum representation to a set of different coordinates, Feynman integral can be represented as a bounded integral of a given volume, here integrated, identified with C, and the integrand is characterized by two elements: a multivalued function that we call U, and that corresponds to a graph polynomial in a generic representation, and eventually a multivalued differential n form that is simply the form that you generate from the product of inverse product of denominator. And in this representation, one can obtain integration by parts identities according to whether the graph polynomial U vanishes or not on the boundary of the integration domain. So Bicop polynomial is one of such, Bicop representation is one of such a representation for which the integration by part identities hold. And this was for us important to identify a few properties of Feynman integral that I'll try to recall in a few moments. Integration by parts identities were studied by Zhang, Larsen, and Li in this representation, and have been implemented in automatic code. As we know, generically, what we expect from integration by parts is not just the equation, but is the solution of the equations of the system. And the solution allows to express a generic integral in terms of a set of denominators that have that may have the same number, a set of integers that may have the same number of denominators as the original one, or lower or simpler one. So the master integral decomposition happened to be extremely useful, and still is, in order to derive differential equation and recurrence relations for master integral as alternative way of determining them. What we know is that when we go on the cut acts as a projector, and eventually maximal cut isolate only the homogeneous term of each identity, either in an IVP or in a differential equation or in a recurrence relation. As a byproduct of this graphical representation, one clearly sees that the maximal cut solution are indeed, the maximal cut are solution of the homogeneous equation, either differential or dimensional shift. Now, for many years, I think we have been puzzling by the idea that the decomposition indeed could be interpreted as coming from a projection. Although found only at the end of the Laporta algorithm of the Gauss elimination to solve the system equation, what we were looking for is really to have the possibility to decompose an integral in terms of a basis, exactly like we do for any vector in a vector space. In order to do that, we need a scalar product and a basis with certain properties, namely a scalar product for the basis that could even allow us to form orthonormal basis, or completeness like relation. So the question to address are what is the dimension of the space that here will be called by nu, and how do we find the scalar product between integrals. And here is the key framework of the RAM theory for twisted cohomology that comes into the game, provide us exactly with the answer that we are looking for. So for a mathematician, integral composed of such a form, integral are pairing of a cycle, integration cycle, which is the dubbed twisted cycle, and a differential form, which is defined as twisted co-cycle. And as you see, for the realm of the function they are interested in, the properties that enable the integration by parts identity to hold are already built in. So in this space, one exploits two properties of the integral, in particular the invariance of the integral under two possible transforms. One is the transform of the integrand, and one is the transform of the integration domain. And if we think two integrals that can generate the same integral, it's interesting to consider the covariant derivative of the multivalued function here that indicate with co-omega, and form a connection, this nabla omega, which is a covariant derivative, or also the anti-derivative, which is performed with U inverse. Owing to these two definitions, we can identify two equivalence classes, in particular for forms that differ by covariant derivative term. In this respect, it becomes natural in this context to play with integrals and the dual integral that differ for the role of the multivalued function u. Okay, for direct integral we have u, and for dual integral we have u inverse. So this equivalence class indeed allow us to define two dual cohomology group formed by the closed forms modulo the exact. And in particular, we can take element from the cohomology and also from the homology group, associated homology group, in order to identify the building blocks of our algebra. I call left form and right form the element of the cohomology group, and twisted contour or twisted cycle and anticycle the element of the homology group. In this framework, there are four possible pairing of these elements. Two of them that we have already seen before that give rise to integral and dual integral. And then there are pairing of cycles that give rise to the topological intersection number, or the intersection number for cocycles, which is the key concept for building integral relation, for instance, for Feynman integrals. Having identified forms and cycles as basic building blocks of our algebra, we can also form two completeness relation or identity resolution. One for forms, one for cohomology classes, and other for contours with homology classes. And here you can see again the intersection number between forms and the intersection number between contours. Now, owing to this toolkit, we can indeed derive two possible identities, type of identity, linear relation acting on forms. So if we consider integrals as pairing of a form and a contour, and then master integral as the pairing with a certain suitable basis of forms, here indicated with EI, the decomposition of a generic integral in terms of a basis can be obtained from the decomposition of a generic form in the space of forms. And this is obtained simply by using one of the completeness relation introduced before. In this respect, then the coefficient of the linear combination is obtained, can be written in terms of a generic projection formula and can be directly evaluated. An additional relation can emerge from, in particular for quadratic relation, if we insert the identity resolution inside the intersection number. Here we use the identity resolution for cycles in the intersection number for forms, and vice versa. We introduce the identity resolution for forms in the intersection number for cycles, and we obtain quadratic relation for integrals. You can see that at the left and the right hand side of those on the right hand side of this identity, there are integrals and dual integrals, and therefore the identity that we obtain, known as Riemann twisted period relation, are indeed the quadratic relation for integrals. So luckily the study, or in particular coming from people in the audience over the year, allowed us to identify and to connect the vector space of differential form to a series of properties, and with a series of geometric properties, all of them converging toward the concept of the dimensions of the cohomology groups I introduced before. Therefore, in this respect, the master decomposition formula becomes the tool, the engineering tool, to derive or to propose the derivation of the identities between the integrals. One starts from the form definition, building the metric matrix, and using it either to build orthogonal form or to directly obtain the coefficient of the relation. The evaluation of the intersection numbers requires is controlled by the geometric properties of U, or actually by the differential logarithmic of U, namely from the graph polynomial in our case. In particular, it's related to the zeros and the poles of omega. In fact, the number of solution of omega equal to 0 corresponding to the critical point, as Lee and Pomeranski had previously introduced, correspond to the number of master integrals, whereas the pole of omega are indeed important to compute the intersection number. The intersection number is the novel ingredient of this development. It's in particular obtained by combining the solution of a differential equation around each pole of omega together with the residue theorem. Eventually, I can answer questions for interested in case afterward about the technical aspect. What's important is that to derive this equation, Stokes' theorem played an interesting and important role. So we try to apply, we applied this toolkit to Feynman integral in Bykov representation, which is the most closely related representation to the Gauss-Aomoto integrals that are the subject of the mathematicians that developed this theory. But what I'm telling is not limited to Bykov representation. In general, other parametric representation can be adopted. So in the application of the decomposition formula, one starts differently from what happens in the application of the integration by parts identities. One needs to choose the basis, and the possible solution that we have been exploring so far are D-log basis or monomial basis according to the case. Additional choice of the basis can be done, and one can eventually study the behavior of the result according to the different choice. Of course, the final decomposition should not depend on the basis. So, two special applications of this formula are the derivation of the dimensional recurrence relation and the generation of the differential equation. The dimensional recurrence relation in this context are simply obtained by a change of basis of master integral. One consider master integral in the original basis EI to be replaced by by a new set of master integral obtained by power application of B on EI. We know that the application of the power of the Bykov polynomial acting on an integral generates higher dimensional integral, and therefore by a suitable change of basis and using directly our decomposition formula, one obtained the recurrence relation for master integral. The system of differential equation obeyed by master integral can be built exactly in the same spirit as the derivation or the definition of the integration by parts identities. In this case, we would use an external connection instead of an internal one. An integral over of an internal connection would vanish. Instead, an integral over instead the action of the external connection over the integral generate a new form, a new differential form, still belonging to the same set of forms that we have been playing with, and therefore we can use the projection formula once again to derive a system of differential equation. The solution of the homogeneous system of differential equation that in the language of maximal cut and momentum space representation, as we said, correspond to the maximal cut, indeed are translated into the element of the in the independent element of the period matrices, which can build by pairing the independent master form with the independent master contours. And the simple this matrix is one of the elements that enters the Riemann-twisted period relation, one side of the quadratic relation for master integral. So in our first work, we applied the intersection number for one forms to build a contiguity relation for a generic class of Lauricella function and to Feynman integral decomposition on the maximal cut suitably chosen to have a univariate representation. And I will sketch just a few examples of diagram giving rise to elliptic solutions, like the two-non-planar, the two-loop non-planar triangle, which has been addressed by several authors also present in the audience. In this case, Bicop polynomial happens to have a quartic form. One can define the omega form and identify that there are 3 zeros, 3 critical points corresponding to 3 independent solutions. These 3 independent solutions can be chosen to be, in this case, we have chosen D-log forms. We built the intersection matrix, and beside obtaining integral relation, we also build a differential equation that, for instance, is canonical. Gamma is the usual exponent of the Bicop decomposition, and it's canonical in gamma. Similarly, also the massive sunrise shares the same feature as the two-loop integral we had described before. And in our first application, we consider maximal cut for different types of integrals. So for us, it was important to have the possibility to reproduce a few limited results, but still non-trivial results, because we were able to obtain the coefficient of the master integral on the maximal cut, even in presence of multiple master integrals. And we understood that in order to push forward our analysis, we need the application of our algorithm to n forms, to deal with n form, and therefore to the calculation of the n variable intersection number. In the literature, intersection number for n forms was available only for logarithmic form, which do not necessarily exhaust the case of integrals related to Feynman amplitude. And revisiting a result of Matsumoto, Sebastian proposed a formula that allowed to compute the intersection number by a global residue theorem. In the most general case, algorithms for generic forms were not available, and therefore we tried to propose the possibility of evaluating it by repeated application of the univariate algorithm in the nested, casting the integral and addressing the integral calculation in a nested representation. In particular, one starts ideally by considering the internal integration with one of the variable and use the projection formula for the univariate in order to express this internal integral in terms of the master integral, and then iterating this procedure, one obtains the full decomposition. Now, in order to apply the iterative approach, it's important to obtain the size of the cohomology group for each level of the iteration, and we were able to connect clearly the result of the dimension of the space proposed by Lee and Pomeranski, namely counting the number of solutions of this system of equation, now to the shape lemma, the same that we used for the maximum cut. Again, the number of master integral is the dimension of the quotient ring between the polynomial in our coordinate with respect to the ideal generated by the D-log form of, eventually by the Jacobian ideal of the omega. So in order to derive in a simple way the multivariate intersection numbers for generic n forms, we adopted an iterative strategy. As said, we consider as known the problem and the decomposition formula at the level n-1, where n counts the number of integration variable, and we want to apply to the extra to the extra dimension, to the extra variable. And nicely enough, you can see here that starting from the intersection number for a n form and inserting here the identity, sorry about that, the identity resolution for the n-1 level in between the two forms, and using the projections formula in the n-1 form, one can obtain the intersection number for the n form out of univariate intersection number recursively. In the solution or in the evaluation of the intersection number is required also the solution of a system of differential equation around the poles. The intersection numbers that we proposed indeed obey an important property. Essentially, intersection number is invariant for forms within the same cohomology group, and which is a property that, for instance, is not valid for the simplified intersection number of the log form. And this property, or better, the exploitation of the cohomology group equivalence class, together with properties of reduced Fuchsian form, was put together by Stefan with an interesting observation in order to simplify the evaluation of the intersection numbers. So in the last few minutes, let me just sketch on a few applications of these ideas, both to multi-valued function, for instance, to the 3f2 functions. And here, as said, we have an integration over two variables, and therefore we need to consider both the subspace, the internal subspace, for instance, Z1, and the external subspace represented by Z1, Z2. The 3f2 have three independent master integrals, which correspond to the number of solution of this system of equation, whereas the internal solution has two master integrals, which we have chosen to have this form, and one can use this form to derive, for instance, contiguity relation for the 3f2 or even the system of equation they obey. Here, for instance, there is the derivation of the system of equation. Again, one could easily obtain canonical systems. We applied it to a few examples of full decomposition of master integral, now going down to all the way through its subtopologies. a simpler case in the one loop, for the one loop box with high power of denominators. Here I leave the steps for questions eventually, and lately we were able to increase a bit the series of application, considering one loop with internal masses or the full massive sunrise decomposition, as well as a few examples at two loop of massless particles, where all these coefficients of the master integral are related, are obtained by intersection number. And in all the cases, we found agreement with public codes giving result for IBPs. Now, the integration by parts identities are an example for Feynman integral of the application of this framework in the case of linear equations. But and I will briefly go to the application of this idea for quadratic relation, in particular for Riemann twisted period relation. In the original paper of Cho and Matsumoto in the mid-90s, they consider among the various examples hypergeometric functions, where the hypergeometric is characterized by this U form, and they picked up these two independent forms, phi1 and phi3, and with this form they built a 2x2 period matrix and dual period matrix by choosing independent integration contour and choosing phi1 and phi3 as independent form. They built the intersection matrix for cohomology, and this is the intersection matrix for homologies. And the Riemann twisted period relation in this case is written like P I inverse P minus equal the intersection number for the cohomology. This is a matricial identity out of which one can extract the individual element, and you see that there are a relation, non-trivial relation, quadratic relation for the Gauss hypergeometric function. In the first case, this is a two-element identity. Here, there is instead a three-element identities. When I saw this formalism, I was caught up by the possibility of applying this to elliptic integrals, and in particular to the complete elliptic K and E function. They are known to obey this formula, the Legendre identity, which can be obtained as a limiting case of a more general identity known Elliott identities for a suitable choice of parameters. And remarkably, this is also an example, can be understood as an example of Riemann period twisted relation upon suitable choice of the basis and of the integration contour. This formalism, I think it's extremely interesting to study and to put it together with what have been the most recent intuition of quadratic relation for Feynman integral that David and Roberts have been proposed, and that also Roman has mentioned during his early talk at this conference, and in particular the conjecture of David and Roberts was recently proved by adopting a certain extension of intersection theory using the Klosterman connection. So I conclude by saying that really the intersection theory seems to provide a new mathematical structure that we can apply to quantum field theory, where the analyticity properties of the integrals are really ruled by the geometry, and in particular by the manifold associated to the graph polynomial of the diagram. So far, it helped us to introduce the novel concept of intersection number, which was a key element to build the scalar product among integrals. One can obtain interesting application both for physics and for mathematics. The chapter is not closed at all. There are many open questions about the suitable representation of Feynman integrals, about regularization of these integrals in this parametric representation, where seems that dimensional regularization is not enough. In the application of our multivariate intersection number, we adopted also analytic regularization, but also it's important to study the structure of the singularity, in particular within the more modern techniques developed by mathematicians, which has to do with the relative twisted cohomologies group ideas. So I'd like just to conclude by sorry, I went back to a few slides, by saying that, going back to my first slide, that addressing a common math problem may really be helpful in make progress, not only in realm of Feynman integrals for particle physics, but we look forward to a more broad range of applications. Thank you very much for your attention.
Thank you for the very interesting talk. Let's take a couple moments to unmute ourselves, and then let's give them a round of applause. It looks like we have a first question from David.
Thank you for the talk. I want to repeat, for historical context in particle physics, where I think the first non-trivial intersection number was discovered in practical physics. I said it at your wonderful conference in Padua, but I say it again. It was by Stefano Laporto about 15 years ago, who was tooling up for the four-loop radiator corrections, the magnetic moment of the electron, and we looked at the three-loop on-shell massive sunrise diagram, and he found there a quadratic relation between what we now understand to be periods and quasi-periods of a modular form. It was an extraordinary thing to me. I'd never thought of quadratic relations between Feynman integrals. And tomorrow, I shall be pointing out how at four loops, such intersection numbers determine the events, the areas of the event horizons of black holes.
Thank you.
Let's see, do we have any other questions? If not, since we're running a little behind, maybe we can just move into the next talk. So the final talk of the day will be Karen Yeats. And so let's welcome Karen Yeats, who will be telling us about the fixing graph theory of Feynman periods.
Hi, so thanks for inviting me, and thanks for coming to listen. I was asked to do a little bit of a review of these Feynman periods, or what people are calling sometimes Feynman periods. So at the very end, I'll say something small that's new and that I'm involved in, but mostly I won't. Okay, so what is it? I'm a mathematician first, so I think I'm going to define something. And here's what I'm going to define. So I want a graph G, because it's that kind of a talk where the first thing you have is a graph. And what do I want to do with this graph? Well, I'd like to sum over all the spanning trees. And then what do I want to do? I want to take the monomial of the edges that you have to cut in order to get that tree. So you have a variable AE for each edge E of the graph G. Okay, and so depending on where you come from, you might call this a Kirchhoff polynomial or a dual Kirchhoff polynomial, or you might call it the first semantic polynomial. But in any case, it's a nice polynomial. And then you might want to write down an integral that uses it. And I sort of want to morally think of it as this integral, But of course, you wouldn't do well in your calculus class for writing down that integral. So I better actually change it a little bit. So let's just integrate over all the variables except for one. And that last one we'll set to 1. So just this guy. This is all we're talking about. So at some level, I don't have to say anymore because we're going to, you know, that's this period and that's what we want to compute. And everything else, I'm actually not going to compute anything because you guys are much better at computing integrals than I am. But what I'm going to do, you might have noticed my affiliation is with the Department of Combinatorics and Optimization, is I'm going to do some combinatorics that tells us some things anyway about this period. And I'm going to overview some of the things that people know about how the combinatorics of the graph tells you something about this period. Okay, it's worth pointing out that this, I mean, it's manifestly written in an appropriate way to be a period in the sense of Kutsevich and Zage, because we're integrating something algebraic over something polynomial, and everything is happily rational, polynomial, algebraic as appropriate. There's a lot of freedom to shift between those things. And these are things that you may have been hearing about for some time. I just wanted to do some examples. So just for people who haven't been playing this game before, we ought to start at the beginning and do some examples. So let's just make a Kirchhoff polynomial. We'll do this graph because there's only so many graphs you can do by hand in a talk without driving everybody crazy. So if I let the edges be A, B, C, and D, I want to sum over the spanning trees. So what are the spanning trees? So AB, for instance, is a spanning tree, which means I put the things that were not the spanning tree in there. AC is also a spanning tree, so I put the BD in there. AD is also a spanning tree, so I put the BC in there. Somehow this isn't the best format for you guys telling me the answer, which is what I would usually do. So I think I would just write the last few terms. You're going to also get the AC and the AD. Okay, and so then you got to integrate that. Well, maybe you're not too happy about integrating that guy because it's got a subdivergence, so it won't converge. But if you do integrate something that does converge, for instance, you might want to take this little guy. That's the first one. And that one sort of famously gives you a 6 Riemann zeta of 3. Okay, so that's the thing that we are talking about. Okay, why are we talking about this thing? Well, or you might say, okay, it's actually really time to go have a coffee or something. For me, it's almost time for lunch. So, because in fact, you know, we already know these things, right? They're part of the story of Feynman integrals. And why are they part of the story? Because, well, you can go look in some textbook that you like that does some Feynman integral calculation. And sure enough, you will see, look, what are these things? They're just your residue. So they're the one part that's always going to be there, no matter what more sophisticated way you use to compute your Feynman integrals, no matter what extra stuff is going on. They're always just sitting there as the residue, independent of your normalization scheme and all these sorts of things. And lots of people have been computing these. And I would particularly note David Broadhurst, who's, I think, still here in the audience, calculated quite a few of them in the 90s in particular. Because it's just this residue, it's in your contribution to your beta function. But of course, these are quite simplified. All the parameters, all the physical parameters are gone. And so higher legs are not going to be interesting. More masses is not going to be interesting. And so higher loops is what is interesting. So this is a loops game. It's worth pointing out that I wrote the parametric form because that's sort of the nicest one from a pure mathematical perspective, perhaps. But of course, it's just this residue of the Feynman integral. So you can write it in any of the ways you're used to writing a Feynman integral. Let me just write some down for you just so you see what I mean. I mean, what can we do? Well, we already wrote the one that was supposed to look like this, right? And I said, oh, it's morally just that. And then I said, well, okay, but it's not really that. And I set one of them to 1. But if you were an algebraic geometer at heart, you probably didn't actually like that, because you'd probably rather think about it as a projective integral. So you the same thing, but let's not set that. But we want to now work over some projective form. And the same holds in other cases. So, maybe I would like to write this thing in momentum space. So then what am I really doing? I've got some product over the edges of the graph, and what do they each have? Well, they each have some momentum of the edge, and then I better square it, and then okay, that's pretty good. And then I could write that affinely, or I could write it projectively. Let's write it projectively first. I guess this is a slightly different. This is like the P version. This would be sort of the A version. And then what would I have to do here? Well, I'd better set one of them to 1. So P1 to a unit vector 1, a bold one, nice bold one, and integrate the rest of them. Subject to my delta functions. Oh, I didn't leave space. Did not leave space. Okay. In fact, let's just not do it that way. There wasn't really space there. Let's not do it that way. Let's do your standard little game. Let's put this back, and then we can just do one for each. We can take a basis of the cycles, so the loops. So then, well, I don't really want to write it all down, but anyway, you know what I want to do. I want to sum over the loop. So I want my PEs to be the sum of the cycles that go through the edge, plus or minus P of the cycle, I should say loop, and then go from there. Okay, so that's fine. And I can also do it in position space, and it's all exactly the same. And in both cases, I can do it in an affine way or not in an affine way, right? So now I'm going to take a product and take an x1, xi minus an xj, and you know exactly what I want to do. And I could do it in a nice projective way, like this. And I could do it in a nice affine way. And I'm going to stop doing this pretty soon because I don't. So better now set some things. Something like that, and then. Okay, fine. You write it whatever way you like. Okay, but why should you care? Because, you already have much more sophisticated ways to think about Feynman integrals. So why should you care? Well, as a physicist, it is a part of what you need, no matter what more sophisticated things you're going to do later. It's relatively computable. And I would argue that pretty well any simplification that you can find that's still got some richness to it, but certainly this one seems to postpone, not remove the interest in complexity, while still making the structure clearer. So I think they're actually very interesting things to study. Now, if I'm going to speak as a mathematician, which is the way I like to speak, I would say what's interesting about this is that it simultaneously looks like algebraic geometry and algebraic graph theory, which are two very nice things. And even more than that, it asks interesting questions that from a pure math perspective, maybe you wouldn't necessarily want to ask. And now that's a general theme, and we've seen that before. We saw that just before in the previous talk, that there are some really nice structures, regardless of how you're thinking about these, that you might want to ask as a physicist. But I'm not so much going to be asking the geometric or looking at the geometric or analytic side of the mathematics. I'm going to focus more on the graph theoretic side of the mathematics. Okay. But of course, you also already know this. This whole talk's about things you already know. No, it's not true. There's some things I think you don't already know later. I'm sure there's one thing at the end you don't know. Because right, since Feynman diagrams began, you use the graph structure to try to help you find the best way to integrate a given graph or find connections between integrals or things like that. And we've already seen examples of that, and you guys know other examples of that. The Feynman periods in particular are good for computing edge by edge, and there's techniques for doing that, and here's a few of them. You can use these graphical functions of Ulrich-Schnitt. So you can use hyperlogarithms, which is closer and related to many of the techniques that we've heard about here. Okay, but now I want to say something concrete about graph structure. I don't want to just say blah, 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 right? There's some graph structure. Of course, there's some graph structure. So what are some specific examples of some of the graph structure? And so I'm going to talk about some of the period invariant graph operations. So things you can do to a graph that don't change this Feynman period or graph period. And the first one we want to talk about is completion. So what is completion? You have to imagine you have some diagram, and you could think of it as a scalar 4-point diagram, right? So there's some sort of diagram, and it's got 4 external edges. And now let's just add a vertex at infinity and connect it to every guy. Okay, that's nice. So I have some sort of vacuum graph now. But then we'll just remove some other vertex. So I'll pick some other vertex in here and I'll remove it. All right. So adding the infinity was the completion, and removing this other guy was the decompletion. And if you think about what's going on in position space, you might be able to see why I'm calling it that. Because sure enough, you're in position space and you can move around where your vertices are. And what kind of freedom do you have? Well, you have a freedom of what you put to infinity, since you can do these affine transformations to your integral. Okay, now these two graphs, they can easily be non-isomorphic graphs. So let's just do a quick example where we're going to get some non-isomorphic graphs. And again, people who've seen all these stories before, I'm sorry that I'm not saying anything that you don't already know and haven't already seen before. So there is a reasonable graph. Let's just use the color to help illustrate. So I'm going to complete it here. And now let's just pick another place to decomplete it. Now I want to pick some place where I'm going to get something different going on. Let's see what we can do. Let's try picking here and see what happens. So if I pick here, that means I'll get rid of this. This is going to go away, and this is going to go away. This is going to go away, and this is going to go away. And so what are we going to be left with? Well, and there's still this guy. So there's actually this triple triangle. There's this edge with 3 triangles coming off it. And now there's another vertex that goes to all 3 of them. And then you're good. So, yeah, these guys are external. Okay, so those are non-isomorphic as graphs, as you would expect, because they're related by completion. Now that's a fairly silly example. If you're thinking now about the actual period, if you've played this game before, you'll know this is a 6 out of 3 fellow here, because it's 2 examples of K4 glued together. And there's many more complicated guys. All right, the next period invariant graph operation is also something that as a physicist you've known for a very long time, because of course we have Fourier transform. And you can use, I mean, what do you do with Fourier transform, right? You just walk into some room full of your people who do quantum field theory, and you say, what are you going to do with your Fourier transform? And what you're going to do, you're going to go between position and momentum space, because that's what Fourier transforms do. But of course, in 4 dimensions, it's kind of nice because you can just reinterpret your position space as the momentum space of another graph, or vice versa. And then what is that on graphs? That's the planar dual of graphs. Because what have you done? You've taken what used to be cycles in the graph, i.e. loops in the sense of quantum field theory. And those are now turning into cuts, right? And the things that used to be, well, you might say, well, what is a cut? I guess I need to say a little bit more. What are the cuts? How should I understand the cuts? Well, if you have a cut in a graph, what is that? That's a set of edges that are momentum conserving. So you have this duality between these cuts, these momentum conserving things, and the cycles. And that is exactly your Fourier transform symmetry or your planar dual. Okay, so that's great. I would just note more generally that you don't actually have to stick to graphs, because of course, you know, you can take a Fourier transform even if the graph was not planar, because you have position and momentum space regardless of planarity. In fact, I think broadly speaking, planarity is a red herring in a lot of this. But then what happens? You don't actually get a graph, you get something else. So this whole story works for regular matroids. What's a regular matroid? Well, some of the regular matroids are the ones that are graphs. Those are called graphic matroids. Some of them are explicitly the ones that are duals, so cographs. Those are the duals of graphs. And then there's a little bit more. And a bit more is a special guy called R10. And I'm not going to say anything else about R10 today, so that's fine. And then you just get to glue these things together in a way that should not seem too surprising from a physics perspective. You basically have something there. I've drawn it as if it's a graph. And maybe it's got a triangle here. And maybe you got something else and it's got a triangle here. But now you join the two triangles together and you remove them. So I can remove them. That's okay. Oh, erase, erase. Oops, erase too much. Just erase just that guy. And then you join them up. And now drawing it that way, it's not clear that that makes any sense on a matroid, but in fact it does. And you can write down what it means and you do that. It's called a three join. We'll come back to three joins in a sec. Now, if you want to operationally work with these guys, you actually find you'll do exactly what you would have done before. So if you think about your Laplacian matrix, well, nobody said it had to be a graph, really. And maybe a better way to see it is to think about your incidence matrix or your signed incidence matrix. And that's the one that you usually write this way. And it's got edges along the top and it's got vertices along this way. And you could write down a matrix like that, but not every matrix is necessarily interpretable as the incidence matrix or the sign incidence matrix of some graph. But as long as it's totally unimodular, so all the subdeterminants are 0, 1, or -1, then it's going to give you a regular matroid. And that gives you enough space to take all the duals you could possibly want. All right, so that's not so much to the point, but it explains at a mathematical level why you're actually just fine doing your Fourier symmetry, even outside of the world of planarity. And you should be, because really this should all be a matroidal story. Okay, you're like, I don't care. What are some other period invariant graph operations? Here's another one. So at this point, to state it more nicely, we should work at the level of the completed graph. And that wasn't the case the previous time, right? Because that extra vertex at infinity and those extra edges going to it, right? You don't want them there in your Fourier transform. So so the planar duality you don't want to do at the level of the completed graph, but you do here. And then this is a really nice one to draw. It looks like this. So here's your graph. There are 4 vertices here. And now what do? You keep one side the same, and you make the other side look like this. Okay, and it takes a little practice to draw that, but anyway. And now these periods are the same. Well, these are the completed guys. So you have to decomplete, and then the periods are the same. And you kind of prove that in a similar way to how you would prove the the completion, right? We said, how do you do the completion? You work in position space and you say, well, actually, I've got these affine transformations, and so I can just put whatever vertex I like at infinity. Poof, done. Well, this one's a little trickier, but it's a similar sort of idea. You put the 4 vertices, you got a freedom to put 4 vertices in a good place. You put them in a good place, and then you have to do a transformation on the one side, but not on the other side. Okay, there's something else that's related to that guy. So what else could you possibly do? Well, let's suppose you're again in that same situation. Okay. Now, we said we're free to put the infinity vertex wherever you like. So let's put it here. So then that guy is not really there anymore. Okay, so now we're really more looking at something that looks like this, and there's just some external edges hanging around, maybe like this. Okay, but now let's suppose one of the sides was planar. So let's take this side and let's do a planar dual. So put a vertex here, put a vertex here, put a vertex here, and then there'll be whatever inside, and we'll do our planar dual. Okay, well, that's kind of nice because we got this side, which has 3 vertices that are special. And we got that other red messy side that's got 3 vertices that are special. So let's just join them back up. And how are we going to do that? Well, look, this guy is in a sort of clearly definable sense opposite to this guy. And so that's where it's going to go. So if I just labeled these guys briefly, A, B, C, then A is the one that ends up here. B, it's opposite to this guy, so B ends up down here. C was opposite to this top guy, so C ends up here. And then we have the red guy on this side. Okay, and now I just have to put infinity back. So put my new infinity, and I have unique places to connect it. Okay, so that's nice. And there's details, lots of details that you want to check, but it works out. What are some other nice graph symmetries? Well, here's another one you might, we already said what a 3 join was. Notice it doesn't say that it's a period preserving thing. The periods are not now equal, but you'll know what the periods are. This is another one that you guys already know, I think, if you play with a lot of these integrals. So say you have that, okay, well, might as well make that be infinity. So really what I'm looking at is this. Okay, and now you're like, yeah, okay, I see what's going on here. The period of this guy is equal to the period of half of it, with just an edge there, times the period of the other half of it, with an edge there. So that's nice. You get some nice product property. And so you might as well think of these as reducible in some sense, and you don't care about them. And so you really only care when there are no small vertex cuts like this. Okay, it's nice. Okay, well, this last one is not telling you the period directly, but it's telling you something about the period. I actually really like this one, even though it's kind of old now. I'm mostly telling you old things. So what is it? Double triangle. So let's say you got a triangle in your graph. Okay. Let's say it connects to another triangle that they share an edge. So here's 2 triangles, they share an edge. And now there's some more graph. And I don't even care if it's 4 regular, but we've mostly been talking about things where it might be. Okay, so there's some more graph. Now what do? You take this middle edge and contract it. Okay, so I contracted that middle edge. What would I do if I contracted that middle edge? I'd get something that looks like this. And this goes like that. And the same rest of the graph is out there. Okay, but I'm not done yet. That's not what I want. I don't like that. That looks yucky. It's not 4 regular anyway. I don't like that. So first of all, I don't really need those doubled guys. Just one is enough. And now these guys are lacking in something, so I'm just going to put a new edge between them. So it looks like that. Depending how you draw it, it can almost look kind of stupid, because drawn like this, I've basically taken a crossing in the drawing of the graph and put a vertex there. But it's not an arbitrary case of turning a crossing into a vertex. It's a very specific one where there's this triangle turning into this pair of triangles. Now that's not a period preserving property, but it does appear to preserve, well, I said transcendental co-weight. What the heck do I mean by that? What's the co? So we've heard about transcendental weight, and in a sort of operational sense, you know what the transcendental weight should be for all of the kinds of functions and numbers you're playing with for doing your Feynman integral calculations, even though the general mathematical question is a much more subtle, but operationally we're fine. We've got it for what we need. Well, that's not even quite true, as some of you know, but close. What do I mean by the co-weight? Well, as you would expect, the numbers, of course, get more complicated as the graph gets bigger, of course, right? You all know that. So by the co-weight, I just mean the difference between the maximum transcendental weight given the loop order of the graph and the actual transcendental weight of the number that you're looking at. And this graph reduction preserves that co-weight. Notice it doesn't preserve the size of the graph, right? The graph has gotten smaller. The number of loops has gone down by 1, but this co-weight is preserved. And I say appears to be, but that's because there are, you know, there's difficulties in sort of figuring out the right way to, well, the point is you can write a precise theorem. It's not just an empirical observation. You can make some precise theorems, but the precise theorems don't quite say that. Of course they can't. They say things about when denominators are 0 and things like that. Of particular interest is this question about the structure of all graphs that reduce to K5. I'd say a little bit more about that in a few minutes. But yeah, I think this aspect of it is very pretty. There's, you've got these Feynman periods, which are a piece of the Feynman integral, and an interesting number theoretically interesting piece, algebraic geometrically interesting piece, also algebraic graph theoretically interesting piece. And here are some nice graph operations that satisfy these things. Okay, I'm going to now move to a related but slightly different topic. So this is a good opportunity to ask if there's any questions now before I move to the next part. All right, the void has no questions.
Yes, I don't see his hand, so I think you can keep going.
Okay. So now I'm going to say something a little bit more specific that I think is very interesting. And it's something that you might have heard me or some other people like Francis Brown or Ulrich Schnetz talk about, which is got called the C2 invariant. So you got to remember your first semantic polynomial or Kirchhoff polynomial. And what do you want to do with it? Well, you have to remember one of the things you could do is put on your algebraic geometry hat. And if you're going to put on your algebraic geometry hat, I once had a PhD student who liked this language of putting on hats. And at one point he was giving a talk and he had found a literal hat somewhere that he decided it was his physicist hat. So he'd take it on and off depending on whether he was speaking as a mathematician or a physicist in the talk. Anyway, I don't have one of those. So what am I going to do? I'm putting on my algebraic geometry hat. And then one of the things I might want to do as an algebraic geometer is I might say, aha, I have an algebraic variety defined by the vanishing of this thing. I'm going to count points on it over finite fields. And so that's what we're going to do. So this here is going to be my notation for the counting points over the finite field of P elements. And if you have played this game before, right, we really are saying FQ or FP rational points on this variety. If you have not played this game before, at an operational level, this is a very simple thing. You just say, modulo P, I have P numbers. I'm going to plug them all in for the variables and see how many times I get 0 modulo P. That's all you're doing. And so in particular, notice it's an affine kind of point count. Okay, then it turns out that as long as the graph has at least 3 vertices, you can always, this is always a number that's divisible by P squared, and then we're going to take that guy mod P, and that's the C2 invariant. This is the thing you want to compute. And so notice that for a given graph, what is C2 really? It's really a sequence, right? There's the C2 at 2 of the graph, sorry, the C2 at 3 of the graph, etc. The C2, 5 of the graph, and so on. Okay. So you think of it as a sequence indexed by primes. You could even put in some prime powers, although we usually don't. So I'm going to just put in a little, you could do a 2 squared. Or you could not, you could stick with the primes. Some of the techniques only work for primes. So. Okay, so this is the thing. All right. Why? Why do you want to study this thing? This seems like a bizarre thing. Again, if you haven't heard this story before. So why do you want to study this thing? Well, this is a little bit of a history story, which again, I know some of you know. So what happened here? People like David Broadhurst and Dirk Kreimer had computed a bunch of these Feynman periods. Not calling them that yet, but you know, computing them because they're nice, useful things to compute in the 90s. And at the time, it looked like they might all be multiple zeta values. At the time, the ones they had recognized then were all multiple zeta values. And it was a plausible conjecture at that time that maybe really everything was going to be multiple zeta values. Maybe by restricting to this period, maybe unlike what I said in an early slide, where the complexities you see in the full quantum field theory are just postponed, maybe it's really simpler and it's just multiple zeta values. Well, it turned out that was false. Many of you know this story. And I mean, it wouldn't be much use for elliptics and beyond if it was only multiple zeta values. But along the way, something very interesting happened, because you say, okay, well, if it were all multiple zeta value, it shouldn't just be because of some stupid coincidence. It should be for some good mathematical reason. Okay. Kontsevich said this, right? Should be some good mathematical reason. What is the good mathematical reason? The good mathematical reason is that the underlying motives, in the sense of algebraic geometry, should be mixed Tate. That's the correct good mathematical reason if what you're seeing is all multiple zeta values. Okay. But in that case, now notice, this is a fact about the geometry of the variety of the Kirchhoff polynomial, right? You're taking an integral over it, you care about the behavior of that integral. So we said already it's a period in the sense of Kontsevich-Zagier, but it's a period in another sense too. It's a period of that variety. You're doing some integral over the variety. Okay. But now, if we want to understand the geometry of that variety, and in particular, if we're not just sort of getting some coincidentally special piece, but if it's really telling us what's going on overall, then we should also be able to access that by looking over finite fields. So, and in particular, if you're in this mixed Tate case, what should happen is that these point counts should be a polynomial. In P. Okay, that's not obvious a priori, but that's part of what this overall mathematical structure tells you, is that if you get all these shoulds lining up, then that's one of the things that you should get. And then in that case, C2 of P is the quadratic coefficient of this polynomial and is the lowest non-zero coefficient. Because we already said this number is divisible by p squared as long as the graph has at least 3 vertices. Well, lowest potentially non-zero. It could be 0, but the lowest, I don't know. At least the smaller ones are 0. That's the 2 in C2. So in particular, it would not be dependent on P. So it's just a constant. Okay, but this is all false. So if they're all multiple zeta, it's false that they're all multiple zeta values, right? This is not true. All multiple zeta values is false. But the should be's all still work, right? So there's still these connections, and some of them are really should be connections, because it's of course possible that when you take this Feynman period, you're not seeing the whole geometry of this variety. So it's possible that it's catching something that's missing the general picture. It's catching something special. But broadly speaking, there still seems to be a lot of use in trying to understand this guy in order to understand the Feynman period. So even though it's false, even still, this C2P is an interesting sort of measure of what sort of things should be going on in PG and its geometry. And again, some of you have probably heard a lot more and you know some of the caveats. There are some interesting caveats here, but it's still broadly speaking an interesting thing. Okay, well, I want to do some graph theory. And I told you a whole bunch about symmetries. Why did I tell you a whole bunch about symmetries? Well, if C2 is supposed to tell you something about the period, you know, it better have the, you better understand what's going to go on with these symmetries, these graph symmetries. And sure enough, the C2 invariant either has or is conjectured to have nice properties for all of these things. It should be completion invariant. I'm going to come back to that one. It should be duality invariant. This is proven in the planar case, Dumitru-Doran. And he proves actually more than the planar case and conjectured in general. There should be a twist invariant. That's conjectured. It depends at least on completion. There should be a Fourier split. The 3 join, it doesn't give a product. It just outright gives 0. And that makes sense if you think about what's going on with the transcendental weight. And in fact, the C2 is, it's sort of seeing the transcendental structure in some nice, well, at least it's giving a hint of it. It's giving a view of it. And so you shouldn't be too surprised to have a double triangle invariance, which was actually one of the first things we proved. It's actually easy. I say it's easy because it's my proof. Of course it's easy. And it's conjectured that if 2 graphs have the same C, no, that's the wrong way around. I wrote the converse. That's the false one. Don't read that. Don't read that. Don't read that. What's conjectured is if they have the same period, then they have the same C2. And what I wrote is false. And the converse is definitely false because, for instance, there's all sorts of stuff that gives 0. And interestingly, it gives 0. Zeros are nice. They're weight drop. Anyway, don't read that. That's actually one thing I like about doing these talks with the pen is that if there's something really stupid on your slide, you can get rid of it. Okay. I wanted to say a few things. Since I'm trying to talk about the graph theory that underlies these things, I wanted to say a little bit about other graph invariants that have these symmetries or that have some things related to these symmetries. And the first one was developed by a PhD student of mine. And unfortunately, I'm not going to say much about it because it seems to be completely useless for physics, which is really too bad because it's got the right symmetries of the period. So you would really think it's got to be telling you something, but we could not figure out what it was telling us. We could prove lots of stuff about it. It's actually much easier to prove stuff about this than it is about C2. So what do? You take a signed incidence matrix, let's just call that E, with 1 row removed. So that's the full rank version. So what is that? E is, remember these are edges, and these are vertices, except there's one extra vertex that we've removed. And what do? You orient all the edges, you put a +1 for one end, a -1 for the other end, and zeros everywhere else. And then if you do that, Well, you could stack these up to make a square matrix. So for the sort of graphs we've been talking about a lot that are 4 regular but with 1 vertex removed, if you stack 2 copies of this up, you'll get a square matrix. And then you can take the permanent of that matrix, and then you say, I don't like permanents. They're bad objects from the point of view of linear algebra. But they're not bad objects if you take them modulo 1 more than the number of copies that you've stacked up. So this you want to take mod 3. And for some other one, you might stack it up a different way, and you take it modulo 1 more than the number of copies you've stacked up. And then it becomes a nice linear algebra object, because that when your matrices have this special form and you take the mod that number, then you're actually back to now having an object that is compatible with row reduction, and so is in fact a linear algebraic object instead of just some sort of thing. Okay, but I'm not going to talk about that because it seems to be useless for physics. Eric Panzer made this HEP invariant, and how did you do that? You take only the dominant term in the Kirchhoff polynomial in each sector, right? So it looked like this, and for any given choice of the variables here, there's going to be 1 monomial that's going to be dominant, and so you just take that. So it turns into, instead it's like the max monomial. This isn't actually notation, but you know what I mean. You take that max monomial. Yeah, you do that guy. Now, this guy is pretty nice, actually. I think it's a really nice invariant, and it also seems to be particularly nice for physics, unlike the permanent, which is not useful as far as we can tell. And it's useful for 2 reasons. So this is all Eric's work. This is not mine in any way. One is that it really looks like it might actually be if and only if. That result that I wrote the wrong way and then I fixed it, but for sure that one's only one way for C2. It really should be if and only if in this case. And also empirically when scaled, it matches the value of the period very well. And some of you have probably seen this from, Eric has given a lot of talks on this. So what is this? This is the HEP, suitably scaled, and this is the period. And all right, look, when you scale them the right way, you get a very nice linear relation. And all right, the right way is a little non-trivial. It's logarithmic on both sides. You have to do a little bit of a loop order scaling, but you get a nice empirical line. Okay, so I'm not going to say more about that. This conference was called Elliptics and Beyond, and so far I have not said anything about any of that. I've just done a little bit of graph theory. So how do we see the elliptics and beyond showing up in any of this story? So first of all, the C2s, they're numbers, and well, in the 90s, they looked like they might all be multiple zeta, but that turned out not to be true. So what are the ones that aren't? Well, okay, elliptics and beyond. That's good. We're finally getting into the topic of the conference. Okay, but this is in the C2 section, so why am I doing that? Because C2 gives us a good way of seeing actually this side of things. Because what C2 sequences do we see? Well, we see constants, 0 and -1. Okay, those are nice. Those are, the 0 are the weight drop guys. And the -1s, well, do you remember how I said these things that came from double triangle of K5, or that's completed, so double triangle of K4, if you're thinking of the scalar 4-point graphs? Those seem to be the -1s. And that's actually another nice conjecture that is sort of a graph theoretic conjecture, which I really like. There's also ones that are almost constant, like they have a problem at p=2, or you need to put in some roots of unity. Then one of the things that gets certain classes of number theorists exciting is you get the modular forms. So okay, that's sort of, we're getting there, we're getting to elliptic here, right? So here's a table of some of the ones that show up. Now, it's a little bit, what the heck is this table showing? It's showing weight and level. Now notice a few of these have been proved, but this is mostly empirical. So a few proven, most are empirical observations. Okay, what do I mean by an empirical observation in this case? I mean, you calculate out the coefficients for C2 a certain ways. You calculate out the coefficients of the Q series of the modular form. Well, you don't, you look it up in a table where somebody else computed it out, and you say, aha, those look the same. Now, some so, and here are the weight and level then of the observed modular forms that you seem to see. Now, this is not just these graphs. We did a lot of these 4 regular, so 5-4 graphs. If you only do the 5-4 graphs, some of this goes away. So these ones in particular, they are only showing up, so far anyway, if you are allowed to go beyond the 4 regular situation. So that's kind of interesting, actually. And this is one of the things, and again, you may have heard other people say this, because this is not my observation, but I think it is one of the interesting observations in this area, is that, okay, what is this? This is the elliptic curve case, right? Weight 2. Okay, but that doesn't show up at all if you stick to 4 regular. So this column here, I've kind of marked it over, but remember those ones were all ones that were not, that required vertices that were degree more than 4. So sticking with vertex degree less than or equal to 4, you get no elliptic curves. And that's interesting. I hope you find that. I think that's very interesting. And you can ask some people who are not me, and I can tell you a few things about that, but there's not really a good understanding of that. Okay, you get various things. Okay. And now that's not everything, because there's also plenty of beyond. There are plenty of unknown sequences, and so if you're really bored, here's a sequence for you. And you can find more of these. There's a paper of Brown and Schnetz about modular forms in QFT. And again, it's a bit older now. This table is actually slightly updated. This table is actually from something I did with Oliver and 2 undergrads, where we did some updated computations. Okay, I have just a couple of minutes left, and I want to say something that's actually my own work. I mean, I have figured in a small way, and some of these other things, actually double triangle is substantially my work too, but here's something new that's my own work, along with one of my master's students, Simone Hu. And this is our theorem. I think this is, and that is that the completion conjecture holds for the prime p equals 2. Okay, and here it is written for the mathematicians, or if you forgot what all this was about, we have a 4 regular graph, K, and 2 vertices. Then we've removed those 2 vertices. Now we've got 2 graphs that are the kind we liked the most, which corresponded to the 4.54 graphs. And we calculate their C2 at 2, and you get the same thing. You get the same residue. Okay. Now, if you heard, a few people will have heard me give talks a year or 2 ago, 3 now maybe, a little while ago, where I could do this in the case where K had an odd number of vertices. And I told everybody at the time that that was clearly an artificial requirement. It was a requirement for the way I was proving it. I did half of this, basically. But then I got a smart master student, and she did the other half. So I'm very pleased about that, because now we can at least say completion holds when p equals 2. Of course, we're thinking about the other values of p. Well, that's a nice result, because I think this completion conjecture really is one of the big open conjectures still in this world. And it's gone to be the point that I think some people are starting to doubt that it's true, just because, you know, smart people have thought about it. Well, Francis, certainly, he's a smart person for sure. I don't know if I should say much about the proof. I think I won't go on to another page. That's the thing to do. Let's just say a little bit about the proof here. It's a different talk, really. It's a nice talk. It's actually totally elementary. I could explain this to all of you. You don't need to know anything sophisticated. It's a beautiful, beautiful proof. But it takes more than 3 minutes. But what is the idea? The idea is you reduce calculating C2 to counting, and now in the p equals 2 case, certain edge bipartitions of the graph. The graph with certain properties. And did I mention I'm from a combinatorics department? I mean, counting edge bipartitions of graphs. I mean, come on, that's like classical, beautiful, just pure enumeration, and it's graph theoretic too. It's really, really nice stuff. Okay, but all right, you can't, okay. And what do we need? We need to count the modulo 2. So what do we need to know? To know that the sets for the two sides have the same parity of the counts. Okay, how can I show that two counts have the same parity? Well, I got to pair them up basically, and it doesn't matter if I pair them up within one of the sets or if I pair them up between the two sets. So I might as well just toss everything into one big set, all of the edge bipartitions for both graphs, toss them all together, and then I want some involution on that set, and that'll tell me, okay, it's even. If assuming, I fixed point free involution, and then I'm done. So find a fixed point free involution. I mean, this is absolutely beautiful classic enumeration stuff. And that's exactly what we do. And at first I couldn't. And that's why I could only do one parity of the number of vertices. So I had to do something more complicated. And once again, I used some really beautiful things that you teach in your second year classes. At least I teach in my second year classes, which is just fun. But Simone finished it. She managed to complete it in the other case. So I did this for some, but I couldn't finish it. Simone finished it. And now I think some people feel that we're never going to get it for higher P, because in the case of general P, they're not bipartitions anymore. They're two P-1 partitions. Partitions into two P-1 parts. And they're not of the edges, they're of P-1 copies of the edges. And that's more annoying. Definitely more annoying. But at some level, that's my area of expertise. My area of expertise is annoying combinatorial things. Because if you look at them long enough, they turn into beautiful combinatorial things. And then if you're lucky, they also help you with your quantum field theory. And that's what I like to do. And here are some examples here at the end of some ways that I've done it, and earlier some examples where other people have been doing that. And I'll stop there.
Thank you for the talk. Let's take a moment to unmute and give a round of applause. I believe David is the first question.
Thank you, Karen. At least one member of your audience was deeply fascinated. I want to make a very modern correction to something that you said. I believe that Eric's conjecture that the het bound is faithful has been disproven by Oliver Schnetz for 3 regular graphs for phi cube theory in 6 dimensions.
Okay. So is it still a live conjecture in the 4 regular case, or does he not?
Yes, I believe so, but that's information. And I then want to make that's a bang up to date comment, further than your knowledge. But I also want to thank you for the historical perspective, but to say that you seriously underestimate the length of my engagement in this subject. In 1985, I wrote a paper on master scalar Feynman diagrams, 5 loops and beyond. I did everything at 5 loops, and I stuck at 6 because I had an irreducible double sum. This is the origin of multiple zeta values. But at that time, in 1985, the referee of the paper said, there are no scalar particles in the world. He hadn't heard of the Higgs boson. There's no phi to the 4th interaction. He didn't know about Higgs work. And no one will ever need to do any calculation to 5 loops in quantum field theory. And we have the 5 loop QC beta function. So if there's anyone around here about the age of 35 who's getting referee reports like that, just wait until you're past 70 and maybe the review of your work will be more favorable.
David, am I allowed to include this thing about the disproved more generally by Schnetz? Because if these slides go up with the annotations, is that okay, or is that still sort of?
Okay. Oliver is attending, and Oliver is not attending, but Eric is. Eric knows about this. Discuss it with him.
Okay. I guess I won't upload my slides right away.
Okay, that should be fine. Our next question is from Pranav Sisla.
Yeah.
Whose name I probably didn't pronounce correctly.
Yeah, you pronounced it properly. Thank you. I had a doubt that is there any type of contradiction between Feynman's path integral and the relativity? Because as we know, if it takes like infinite velocity or infinite amount of velocity to go from a finite position to infinite position, which actually in the theory of relativity, it says that you cannot cross the speed of light. So I saw this somewhere in the internet a few days back. I wanted to know if there is some kind of contradiction or not. I don't know if the question is valid or not, but I checked it in the internet. I got it in the internet.
The question isn't really applicable to this conference, but Karen, if you want to say something, sorry.
No, I don't think I was going to have anything to say other than that. Yeah, these calculations are not speaking to that in any direct way. We're looking at it of an individual.
I know. I just wanted to clarify if you knew about it or something. Like I knew that this wasn't related to this, but it was pestering in my mind for a while.
I don't have anything to add to that at the moment.
Okay, thank you.
I can maybe find you some resources later. Let's see. There's no other hands risen right now, but I did have a question about the C2 invariant, or I guess more broadly, whether, since the C2 invariant has got this very nice way to indicate weight drop, to indicate ellipticity, or anything like that, not for Feynman periods, but for more general Feynman integrals, as in if you add kinematics, is there any hope that there's some object that has these properties?
Yeah, I mean, I think there's hope, but I don't have a concrete thing to say right now. I don't know if David has something he would add to that. He might be the one who would have a good concrete idea. The thing is, so here's how you would try to find something like that. You would say, okay, again, you have to put on your algebraic geometry hat for a second. You say, as an algebraic geometer, where is this coming from? And then once you've found where it's coming from as an algebraic geometry, you say, can I access that in some other way that's maybe a discrete way? Because that's part of what C2 is doing, is because it's discrete, it has some advantages for computing, say.
Okay. David, you were trying to say something. Go ahead.
I think what Eric is doing at present is really very important. Karen referred to it in this graph. The Hep bounds, which you can, are essentially combinatorial objects, they are rational numbers, that they are wonderfully accurate predictors of the actual values of these amazingly complicated integrals, whether they be elliptic, Calabi-Yau, quantum field theory will outgrow any mathematical attempt to contain it. You go to enough loops and you've found some new object down here. But I think what Eric has done here is actually show that there's a combinatoric, a rational, we're plotting immensely difficult to calculate graphs against rational numbers here. I think this is just an extraordinary thing. Now, the person that is most likely to exploit this is Misha Berinsky, who has developed a Monte Carlo algorithm for multi-loop diagrams, and by multi-loop I mean 20-loop diagrams, which are absolutely impossible by sector decomposition, using Eric's Hep bound to determine the Monte Carlo sampling. And he can calculate 20-loop Feynman diagrams to 5 significant figures by sampling only 10 to the 10 points using this. So there's something really, really important going on. It's still at the level of the simple single scale periods that Karen's been talking about. It has prospects, and Mishy's most recent paper shows this applications. But we have something here that's developed just in the last couple of years with these two wonderful young people, Eric Panzer and Misha Berinsky, that can give you 5 significant figures of a 20-loop Feynman diagram in a few minutes. That's big news.
Thank you. It's fascinating. Let's see. I don't see any more hands raised. So in that case, we can thank Karen again, and I'll see you all tomorrow, either tomorrow morning for those who the time zone works out, or otherwise for the talks tomorrow afternoon. Thank you all.